Somewhere in the ice sheets of Greenland, buried under thousands of feet of frozen history, there's a rhythm, a heartbeat, a clock that's been ticking since before Rome existed, before the pyramids, maybe before humans even learned to write. And here's the unsettling part. That clock appears to reset human civilization every 1,500 years, give or take. Not randomly, not occasionally, on a pattern so consistent that scientists studying ocean sediments and ice cores keep finding the same signature over and over again, like a fingerprint left at the scene of countless collapses. And if this pattern is real, if this rhythm actually governs something as massive as the rise and fall of entire civilizations, then here's the question that should keep you up at night. When did the last one start? The answer might surprise you. Around 1,200 years ago, right around 800 CE. Which means if the cycle holds, if history really does repeat on this kind of timescale, we could be approaching the edge of another one right now. Think about what's tied to this rhythm, the late Bronze Age collapse, when a network of powerful empires across the Mediterranean and Near East, cultures that had thrived for centuries, simply vanished within a few generations. The fall of Rome, an empire that seemed unshakable, brought down not just by invasions and politics, but possibly by drought, crop failures, and a climate that turned against it at exactly the wrong moment. Even the Vikings, those legendary seafarers who conquered the North Atlantic, may owe their explosive expansion to a warming climate that opened up the seas and made their voyages possible in the first place. Coincidence? Maybe. But scientists like Gerard Bond, who we're going to talk about in a moment, found something in deep ocean sediments that suggests this isn't coincidence at all. It's a pattern, a cycle written into the physical record of our planet, hiding in layers of rock and ice, waiting for someone to notice it. And once you start looking for it, you start seeing it everywhere. Ancient civilizations rising during periods of climate stability, then crumbling, right as the pattern shifts into a colder, harsher phase. Migrations, famines, plagues, all clustering around the same turning points in this 1,500-year rhythm. Like the planet itself has a pulse, and every civilization that's ever existed has had to survive its beat. Now, if you're listening to this late at night, maybe with your eyes half closed, drifting off to the sound of my voice, that's exactly why I make these videos. So do me a favour, subscribe if you haven't already, and tell me where you're listening from and what time it is right now. I read every comment, and it's honestly one of my favourite parts of doing this. Last week alone I saw London at midnight, Sydney at sunrise, and someone in Toronto listening on their lunch break. All of you, scattered across time zones, tuning into the same story at completely different moments. There's something oddly beautiful about that, and if you want to support this channel in the easiest way possible, follow the show on Spotify. The link's right there in the description. It costs you nothing, takes about 2 seconds, and it genuinely helps more than you'd think. Because what we're about to dig into here, this hidden 1,500-year rhythm, connecting ice cores, ocean sediments, and the rise and fall of entire empires, might be one of the most important patterns hiding in human history. We're going to trace it from its discovery by a geologist who almost didn't believe his own data, all the way through the collapse of the Bronze Age, the fall of Rome, the mysterious dark cloud that blotted out the sun in 536 AD, and the Viking Age that followed right after this last cycle supposedly began. And by the end we're going to ask the question nobody really wants to answer. Are we due for another one? So who was the man who actually found this thing? Not a historian, not an archaeologist digging through the ruins of some fallen empire. A marine geologist named Gerard Bond, working out of Columbia University's Lamont Doherty Earth Observatory, spending his career doing something that sounds on the surface almost mind-numbingly tedious, pulling up mud from the bottom of the North Atlantic Ocean. But that mud, it turns out, was a time machine. Here's how it works. Every year, layer upon layer of sediment settles onto the ocean floor. Dust, dead plankton, volcanic ash, and crucially tiny fragments of rock and mineral that get carried out to sea by icebergs. When an iceberg breaks off a glacier and drifts out into open water, it's not just ice. It's carrying debris, rocks, and grit that got scraped up when the glacier was grinding across the land. As that iceberg melts, all that debris rains down to the ocean floor, settling into the sediment in a very specific, very traceable way. Scientists call this ice-rafted debris, and normally you don't find much of it. Icebergs mostly stay up near the poles, melting before they ever make it very far south. But every so often, throughout Earth's history, something changes. The climate cools, more icebergs break off. And instead of melting near Greenland, they drift much farther south before finally dissolving, scattering their rocky cargo across a much wider stretch of ocean floor. Bond and his team spent years drilling cores out of the North Atlantic seabed, essentially pulling up long cylinders of compressed history and examining the layers under a microscope. And what they found was strange. The ice-rafted debris wasn't randomly scattered throughout the sediment. It showed up in distinct bands, pulses of debris separated by long stretches of relatively debris-free sediment. Like tree rings, except instead of marking years. These bands seemed to mark entire climate events, moments when the North Atlantic had gone through a serious cold snap. And when Bond and his colleagues started measuring the spacing between these bands, they noticed something that shouldn't have been there. The pulses weren't random. They kept showing up at intervals of roughly 1,500 years, give or take a few centuries. Cold pulse. Warmer stretch. Cold pulse again, over and over, stretching back through the sediment record for tens of thousands of years. This was published in the late 1990s, and it landed like a genuine shockwave in the climate science community. Because up until that point, most scientists assumed that the climate of the current geological period, the relatively stable, relatively warm stretch we've been living in for the last several thousand years, was basically just that, stable. Sure, there were the big glacial cycles, the ice ages that came and went over tens of thousands of years, driven by predictable wobbles in Earth's orbit. But within those broader cycles, the assumption was that things had settled down. No major surprises, no hidden rhythms ticking away in the background. Bond's data suggested something completely different. It suggested that even during our current warm period, the one that allowed agriculture, cities, and eventually civilization itself to emerge, the climate has never actually been fully at rest. It's been pulsing, quietly, on a cycle of roughly 15 centuries, like a heartbeat running just below the surface of recorded history. These recurring cold pulses eventually became known as Bond events, named after the man who first identified them. And once researchers knew what to look for, they didn't just find this pattern in one ocean core. They found it in multiple cores, pulled from different locations across the North Atlantic, all showing the same spacing, the same rhythm, the same eerie consistency. Now, naturally, when you make a claim this big, that there's a previously unknown 1,500-year climate cycle hiding inside what everyone thought was a stable interglacial period, the scientific community doesn't just nod along and accept it. Bond's findings faced serious pushback. Critics pointed out that ocean sediment can be messy. Currents shift. Sediment gets disturbed by underwater landslides, by burrowing organisms, by all sorts of processes that could scramble the layers and create the illusion of a pattern that wasn't really there. Some researchers argued the spacing wasn't as regular as Bond claimed, that you could find similar intervals almost anywhere if you were looking hard enough for them, a bit like seeing shapes in clouds. But then something happened that's incredibly rare and incredibly powerful in science. Other lines of evidence, completely independent of Bond's ocean cores, started showing up with the same signature. Ice cores drilled out of Greenland, layers of compressed snow going back tens of thousands of years showed corresponding shifts in temperature and atmospheric dust that lined up with Bond's cold pulses. Cave formations in places like China and the Middle East, stalagmites that grow layer by layer and can be dated with incredible precision, showed matching shifts in rainfall patterns at roughly the same intervals. Lake sediments in Europe, tree ring records, even solar activity reconstructions based on isotopes that form when cosmic rays interact with the atmosphere started lining up with the same rough 1,500-year spacing. This is what scientists call corroboration from multiple independent proxies, and it's about as close as you can get to certainty in a field like paleoclimatology. One data source might be a fluke, two might be a coincidence. But when ocean sediments, ice cores, cave deposits, and solar records all point toward the same recurring rhythm, you're not looking at noise anymore. You're looking at something real. This discovery genuinely reshaped how climate scientists think about long-term stability. For decades, the working assumption had been that our current climate period, the one civilization has depended on entirely, was fundamentally calm compared to the wild temperature swings of the ice ages. Bond's work suggested that calm was relative, that underneath the surface there was still a rhythm playing out, a series of coolings and warmings that, while nowhere near as extreme as a full glacial cycle, were still significant enough to shift rainfall patterns, disrupt agriculture, and destabilize entire regions. And here's where things get genuinely unsettling, because once researchers started mapping these Bond events against the historical timeline, against the actual dates when major civilizations rose, thrived, and then often quite suddenly collapsed, the correlations were hard to ignore. Could a natural climate rhythm buried in ocean mud for thousands of years actually explain some of the biggest turning points in human history? Could the fall of the Bronze Age empires, the collapse of Rome, even the mysterious dark centuries that followed, all trace back to the same pulsing rhythm Gerard Bond found hiding in the North Atlantic seafloor? That's the question that would end up driving decades of research that followed. And to understand how scientists actually connect a layer of mud on the ocean floor to the collapse of an empire thousands of miles away, we need to look at exactly how they read these ancient climate signals and what they've learned about the mechanisms driving this rhythm in the first place. If you want to claim that a cold snap in the North Atlantic helped topple a kingdom in Mesopotamia or triggered a famine in China, you need more than a suggestive line on one graph. You need a way to actually read the past climate with the kind of detail historians use to read old chronicles. That's what paleoclimatologists do. Their archives aren't libraries or stone tablets. They're ice, mud, rock, and wood, and each of those keeps its own kind of memory. Start with the purest time capsules we have, the ice cores. In Greenland and Antarctica, scientists drill down through ice sheets that are miles thick, pulling up cylinders of ice that record snowfall year after year, going back more than 100,000 years in Greenland and over 800,000 in Antarctica. Each layer began as snow, fallen in a particular winter, in a particular atmosphere, under a particular sky. As that snow is buried and compressed, it traps tiny bubbles of air. Those bubbles are literal samples of ancient atmosphere, sealed and stored like microscopic fossils. When researchers slice through an ice core, they can measure how much carbon dioxide and methane were in the air, what kinds of aerosols and dust were swirling around, even whether there were volcanic eruptions darkening the skies. The ice itself holds clues too. The ratio of heavy to light oxygen atoms in the water molecules shifts depending on temperature. Warmer air tends to evaporate and carry more of the heavy isotopes, colder air less. By analysing those ratios layer by layer, scientists can reconstruct a temperature curve that rises and falls through time. When those curves show repeated cooling spikes every roughly 15 centuries, And those same spikes line up with Bond's pulses of iceberg debris in the North Atlantic. You're not just guessing anymore. You're watching the same heartbeat through a different organ. But ice cores aren't the only record. Remember that ocean mud Bond worked with? It doesn't just store rock fragments from icebergs. It stores a whole cast of microscopic witnesses. Each layer of sediment on the seafloor contains the shells of plankton and tiny organisms called foraminifera. Different species thrive in different water temperatures and salinities. The chemical makeup of their shells shifts with the water around them. When paleoclimatologists analyze those shells, they can tell whether the surface ocean was warm or cold, fresh or salty, calm or stormy when that layer was laid down. Add in the ice-rafted debris itself. Those distinctive mineral fingerprints carried out to sea by melting icebergs, and you get a detailed record of when the North Atlantic was spewing ice far to the south and when it was relatively quiet. Each thick band of foreign rock fragments is like a flag. Something big just happened in the North Atlantic. Now take that ocean record and walk it onshore. Trees don't live for hundreds of thousands of years, but they are incredible witnesses to the last few millennia, which is exactly the span where we want to compare climate rhythms with the rise and fall of civilizations. Every year, a tree in a temperate climate adds a new ring of growth. In a good year, plenty of rain, mild temperatures, that ring is wide. In a bad year, drought, cold snaps, it's narrow, sometimes barely there. Dendrochronologists, the scientists who study tree rings, can match these patterns from living trees to old beams in buildings, to buried logs, to petrified stumps, creating continuous timelines that can stretch back 10,000 years or more in some regions. Those ring-width patterns don't just tell you if a year was good or bad. Combined with the chemistry of the wood, they can reveal whether a region was unusually dry, unusually cold, or slammed by repeated extremes. When those tree-ring droughts line up with cold phases seen in Greenland ice, and with Bond events in the ocean mud, you're seeing the same event echoed in forests, separated by continents. Then there are the caves, in places like China, Oman, and the Mediterranean. Water dripping through limestone caves builds stalagmites and stalactites, collectively called speleothems, layer by layer over thousands of years. Each layer forms from water that percolated down from the surface, carrying dissolved minerals and a chemical signature of the climate above. The key again is isotopes. The ratios of oxygen and carbon isotopes in those calcite layers shift with rainfall amount, monsoon strength and temperature. Uranium-thorium dating lets scientists pin those layers down in time with astonishing precision, sometimes to within a few decades over spans of many thousands of years. When speleothem records from, say, a cave in China show recurring weakening of the Asian monsoon, around the same times that North Atlantic sediments show a Bond event, and Greenland ice shows a cooling, that's three completely different archives, all with their own physics and chemistry, telling you that something synchronized the climate system on a hemispheric scale. This is the core of the method. Paleoclimatologists live and die by cross-checks. No single proxy is perfect. Ice layers can get folded or disturbed. Ocean sediment can be smeared by currents. Tree rings only record what's happening where the tree is planted. Cave growth can pause or speed up. Each archive has noise, local quirks, and potential distortions, so scientists don't trust any one of them on its own. They line them up in time using independent dating methods, radiocarbon for organic material, annual layers for ice and some lake sediments, uranium-thorium for cave formations, known volcanic ash layers as benchmarks, where they appear in multiple cores. Then they ask, do different proxies from different places show changes at the same times, pointing in the same general direction? If an apparent 1,500-year cycle only existed in one ocean core, it would be suspicious. But when the timing of Bond events shows up as cold phases in Greenland ice, as shifts in speleothem rainfall, as stress in tree rings, and as reorganizations of ocean biology in plankton shells, it stops looking like pattern seeking and starts looking like a real underlying signal. And this isn't a casual eyeballing it on a graph kind of exercise. Teams run statistical tests to see whether the apparent rhythm is stronger than what you'd expect from random fluctuations. They test different dating assumptions, different ways of stacking and aligning records. They look for the same signal in archives that were collected and processed by completely different groups in different countries using different instruments. That's why, even though there's still debate about how regular and how global the 1,500-year cycle really is, the idea hasn't just vanished as a curiosity from the 1990s. Too many independent lines of evidence keep hinting at the same recurring pulses. They might be messy. They might drift by a few centuries. But they're hard to dismiss, which naturally leads to the next question. What on earth could be driving such a persistent rhythm? It's one thing to see a heartbeat in the data. It's another to figure out what's acting as the pacemaker. For that, we have to look beyond the archives and start examining the engine room of the climate system itself. The sun, the oceans, and the feedback loops that connect them. If you want a 1,500-year rhythm, the first suspect you grab by the collar is the sun. After all, almost all the energy in Earth's climate system ultimately comes from that one star. Change the sun, change everything. We know the sun isn't perfectly constant. It pulses and flickers in subtle ways. The most familiar pattern is the roughly 11-year sunspot cycle. More sunspots generally mean a slightly brighter sun. Fewer sunspots, a slightly dimmer one. Over centuries, those short cycles stack into longer fluctuations, grand maxima when the sun is unusually active, and grand minima when it goes quiet, like the Maunder minimum in the 1600s, which lines up eerily well with some of the coldest decades of the Little Ice Age. But here's the catch. The direct change in total solar energy over these cycles is small, on the order of 0.1%. Not nothing, but not the kind of sledgehammer you'd expect to swing global climate into repeated cold shocks and reorganize ocean circulation. So some researchers think the sun is less like a hammer and more like a metronome. Its small rhythmic nudges might be enough to push a very sensitive system, the North Atlantic, over a threshold again and again every time other conditions line up just right. To understand how that could work, you have to follow the heat into the ocean. The Atlantic isn't just a big blue puddle, it's part of a global conveyor belt of water, driven by differences in temperature and saltiness, what oceanographers call thermohaline circulation. Thermo for heat, halin for salt. Here's the basic idea. Warm, salty surface water flows northward from the tropics into the North Atlantic. As it moves, it gives off heat to the atmosphere. That's one reason winters in Western Europe are milder than you'd expect for their latitude. Eventually, near Greenland and the Nordic seas, the surface water becomes cold and dense enough that it sinks, plunging down into the deep ocean. That sinking helps pull the whole conveyor along. The newly formed deep water then creeps southward along the ocean floor, eventually upwelling in other parts of the world and completing a loop that can take 1,000 years or more. As long as this conveyor is running smoothly, it acts like a vast heat pump, moving warm water north and moderating the climate around the North Atlantic. But it has an Achilles heel, fresh water. If you dump a lot of fresh water into the North Atlantic by melting ice sheets, by increased rainfall, by redirecting massive river flows, you dilute the salt. Less salt means lower density. Lower density means the surface water doesn't want to sink as easily. If enough of the sinking slows or stops, the conveyor belt can weaken dramatically, or even reconfigure into a different pattern. That's not just a theoretical cartoon, The climate record is full of episodes where huge bursts of fresh water appear to have slammed into the North Atlantic and knocked the circulation sideways, triggering abrupt coolings over Europe and North America. Now connect the dots. The Bond events you met earlier, those layers of ice-rafted debris scattered across the North Atlantic sea floor, are basically fingerprints of times when the northern ice margins got unstable and started shedding icebergs far south of their usual range. Every one of those events is also, by definition, a pulse of fresh water. All those icebergs eventually melt. So one leading theory goes like this. There is some internal oscillator in the North Atlantic climate system. Over centuries, slow changes in ice volume, ocean salinity, and heat content gradually bring the system closer to a tipping point. Then some relatively small nudge, a weak solar period, a run of wet decades, a volcanic cluster pushes it over the edge. Ice margins destabilize. Icebergs surge. Freshwater floods the North Atlantic, the conveyor weakens, and the region cools abruptly. Once you've knocked the system into this cooler state, new feedback loops kick in. Colder water allows more sea ice to form. Sea ice is bright. It reflects more sunlight back into space than dark open water. More reflection means less absorbed solar energy, which reinforces the cooling. Expanded sea ice can also act like a lid, blocking heat exchange between the ocean and atmosphere, and changing wind patterns. Meanwhile, the weakened conveyor is delivering less warm water northward, so the North Atlantic stays cold, which helps preserve both sea ice and land ice. That in turn can keep the freshwater flux going for a while, as glaciers and ice shelves continue to calve. But it doesn't last forever. Over time, the freshwater pulse subsides. The ocean slowly resalinizes as evaporation and inflow from saltier waters rebalance the system. Sea ice retreats. The conveyor regains strength. Northern regions warm again. The climate flips back toward a more stable, milder mode. In this view, the 1,500-year beat isn't carved into stone by the sun. It's more like the natural period of a wobbly system, the rough timescale it takes for the North Atlantic to drift toward instability, flip, and then relax back, under the combined influence of ice sheets, ocean mixing, and background solar variability. But not everyone agrees on the script, or even on the cast of main characters. Some scientists argue that the 1,500-year signal might be largely internal to the ocean ice system, with the sun playing only a supporting role or none at all. In their models, random clusters of storms, shifts in sea ice cover, and chaotic ocean eddies can, over centuries, self-organize into quasi-periodic swings without any neat external pacemaker. Others lean more heavily on solar variations, not just in brightness, but in ultraviolet output and the solar wind, which can influence the upper atmosphere and potentially, through a cascade of effects, cloud cover and storm tracks. In that story, even tiny periodic flickers in solar activity can be amplified by atmospheric and oceanic feedbacks into the bigger climate pulses we see in the proxies. Then there's the argument about scale. Do these Bond-style oscillations represent a truly global rhythm, driven by a single mechanism? Or are we seeing a North Atlantic-centric cycle that happens to project into other regions in complicated ways? Some records in the Southern Hemisphere and the Pacific line up neatly with 1,500-year events. Others don't. Some models reproduce the cycle when they include detailed North Atlantic physics. Others struggle. So far, there is no final verdict. What most researchers do agree on is this. The climate system contains powerful feedbacks involving ice, fresh water, and the Atlantic overturning circulation. These feedbacks can turn small, slow nudges, whether from the sun, from gradual CO2 changes, or from random internal wiggles into sharp, sometimes abrupt shifts. And over the last 100,000 years, Those shifts seem to have clustered again and again around that haunting 1,500-year timescale. Think of it as an unsolved case with a thick file and lots of suspects, but no single smoking gun. The sun leaves fingerprints, the ocean conveyor shows up at multiple crime scenes, ice and fresh water keep appearing near the bodies. Different detectives emphasize different clues, but nobody has put together a theory that explains every piece of evidence at every time in every place, which in some ways makes the story more unsettling. Because even without knowing exactly what flips the switch, we can see the consequences when it does. The next step is to watch one of those flips happen in real time, or as close to real time as Earth's climate allows. To do that, we roll the clock back to one of the sharpest, strangest resets of all, a time when the North Atlantic went from warming to deep freeze in just a few years and dragged half the planet along with it. The event that marks the first clear tick of this cycle in the world of human myth and memory, the Younger Dryas. 12,900 years ago, the world was finally thawing. Ice sheets that had smothered North America and Northern Europe for tens of thousands of years were in full retreat. Temperatures were climbing out of the last glacial maximum. Forests were marching north. Big rivers fed by melting ice were roaring across continents, dumping sediment into the oceans. In the Levant, in what is now Syria, Lebanon, Israel and Jordan, small groups of hunter-gatherers we call the Natufians were experimenting with something almost unthinkable for their Pleistocene ancestors: staying put. They were building semi-permanent villages, harvesting wild cereals with flint sickles, storing grain in pits. In a few places they were even putting up stone foundations, the architectural ancestors of houses. If you were one of them, it would have felt like the world was finally calming down. After an age of ice and migration and scarcity, the climate was turning kinder and more predictable. Winters were milder, growing seasons longer, plants and animals followed more reliable rhythms. And then, in the span of a human lifetime, the climate snapped. This is the Younger Dryas. Just as the last ice age seemed to be ending, global warming slammed into reverse, abruptly. In Greenland ice cores, you can trace it layer by layer. Isotopes that track temperature show a sharp inflection. Within maybe a decade, possibly just a few years, temperatures over the North Atlantic region plunged back to near glacial levels. Not a gentle pause, a cliff. Average temperatures in parts of northern Europe may have dropped 5 to 10 degrees Celsius. That's the difference between modern southern France and northern Siberia, delivered over the course of a single childhood. Glaciers that had been shrinking stabilized and, in some regions, advanced. Sea ice in the North Atlantic spread southward. In Europe, pollen records show forests retreating, replaced by cold-tolerant shrubs and tundra plants. In the eastern Mediterranean, rainfall patterns shifted, lakes shrank, and drought-prone intervals increased. The warming world that had seemed like the new normal turned out to be a brief intermission. For humans already on the landscape, this was not an abstract climate event. It was a total reorganization of the rules of survival. Reindeer, elk, and other cold-adapted species regained ground. Animals that had followed forests north found their ranges squeezed. Plant species shifted their ranges upslope and southward. Migratory pathways bent and broke. If your people depended on a certain herd's regular crossing, a certain stand of nut-bearing trees, a certain marsh where birds nested every spring, that reliability vanished. For the Natufians, the shock is written in the dirt. Before the Younger Dryas, their sites show increasing sedentism, heavier grinding stones, more storage pits, evidence of investment in place. As the cold and dryness set in, some of those villages were abandoned. Others shrank. People seemed to have gone back to being more mobile, chasing scattered resources along wider territories. And yet, paradoxically, this crisis may have pushed humanity over one of the most consequential thresholds in our species' story: agriculture. In the Levant, just after the Younger Dryas, we start seeing clear signs of deliberate cultivation of cereals like wheat and barley, not just harvesting wild stands, but planting, tending, selecting seeds. One influential hypothesis argues that as the Younger Dryas made wild food sources less predictable, shorter growing seasons, more erratic rainfall, people who had gotten used to the relative abundance of the preceding warm period were unwilling to simply revert to older, leaner ways of life. Instead, they doubled down on control. You can imagine the pressures: declining yields from wild stands of grain that had been reliable for generations, more competition between local groups, children who had grown up in semi-permanent villages not wanting to abandon their home valleys. Under those conditions, anyone who could coax a little more food out of a patch of land, by weeding, watering, saving the fattest seeds, had a crucial advantage. Over centuries, those small incremental nudges, tending here, planting there, turned into domestication. Grains evolved to stay on the stalk instead of shattering in the wind, making them easier to harvest but more dependent on humans. People evolved cultural habits, tools and social structures organized around fields instead of game trails. In this way, the Younger Dryas wasn't just a cold snap. It was a reset. It cut short the easy trajectory from Ice Age hunting grounds to a gently warming Holocene paradise. It forced a test of human flexibility right at the moment when we were beginning to settle down. And we responded, not just by moving and adapting our hunting strategies, but by rewiring our relationship with plants, animals, and landscapes. What caused such a violent lurch in the climate at exactly that moment? Here, the science is still arguing with itself. The mainstream view centers on the same fragile machinery we just explored, the North Atlantic's overturning circulation. As the North American ice sheets melted, they didn't just disappear politely. They poured staggering amounts of fresh water into the ocean. One candidate is the sudden rerouting of a meltwater torrent called the Laurentide Ice Sheets Proglacial Lakes, especially a giant one often called Lake Agassiz. As ice dams gave way, enormous floods of fresh water may have surged into the North Atlantic. That flood would have diluted surface salinity, weakened the sinking limb of the conveyor, and choked off northward heat transport. Europe, Greenland, and nearby regions would have felt the hammer first, but knock-on effects rippled through the global circulation. The timing in some records fits well. Big meltwater pulses just before the onset, followed by centuries of cold. But there's another, more dramatic suspect on the board: an impact. Some researchers argue that a comet or fragmented asteroid exploded over the Laurentide ice sheet or nearby regions right around 12,900 years ago. They point to layers of sediment with unusual signatures: tiny glassy spherules, spikes in platinum, burned organic material, and what they interpret as shocked minerals. In their version of the story, the impact would have devastated ecosystems, ignited wildfires across continents, destabilized ice margins, and triggered a rapid freshwater pulse into the oceans, kicking the climate into Younger Dryas mode. It's a bold hypothesis, and it has plenty of critics. Some labs haven't been able to replicate certain findings. Alternative explanations for many of the supposed impact markers exist: ordinary wildfires, volcanic sources, redeposited older materials. At this point, the idea of a Younger Dryas impact is intriguing but far from settled. There's also a more modest possibility that the climate system was already teetering, with meltwater slowly accumulating in key regions, and only a relatively small additional nudge, maybe a cluster of volcanic eruptions, maybe a solar downturn, Maybe just a particularly unlucky run of atmospheric circulation patterns pushed it over the edge. What's important for our story isn't picking a single villain. It's recognizing the pattern here. At the dawn of what we think of as our world, the Holocene, the age of villages and farms and cities, we see a sharp, abrupt climatic reset centered on the North Atlantic. It arrives fast, lasts about 1,200 years, and then ends just as abruptly, giving way to the stable warmth in which agriculture, writing and civilization will later bloom. In other words, right at the edge of myth and memory, the climate throws humanity a curveball on a timescale of centuries to a millennium, and we respond by reinventing ourselves. The Younger Dryas becomes our first clear, high-resolution example of the kind of event that will echo through the rest of this story. A sudden shift in the planet's thermostat that doesn't just change temperatures, it punts human societies onto new trajectories. Once you see it that way, later RESETS stop looking like isolated disasters and start looking like points along a repeating curve. Because the Younger Dryas isn't the last time a cold, dry century-scale shock will coincide with human systems on the edge of transformation. A few thousand years later, as the first true cities begin to rise between the Tigris and Euphrates, another great lurch in the climate will test them. That one we call the 4.2 Kiloyear event. And it too looks suspiciously like the tick of a very old clock. 4,200 years ago, the experiment that began after the Younger Dryas had reached its first real crescendo. Agriculture was no longer a fragile innovation. It was an entrenched way of life. Along the Nile, the Tigris and Euphrates, the Indus and its tributaries, generations had lived and died under the assumption that the rivers would rise, the rains would come, and if you organized your society correctly, grain would follow. Kings and priests had built their legitimacy on that assumption. They didn't just rule people, they were brokers with the sky. And then again, the climate snapped. This time not back into ice, but into something just as lethal for settled civilizations. Deep, persistent dryness. Geologists give it a sterile name, the 4.2 Kiloyear event. In practice, it was a megadrought that left fingerprints from Africa to China. In speleothems, cave stalagmites, from Oman and Iran, you see it as a sudden shift in oxygen isotopes, a signal that rainfall dropped sharply and stayed low for centuries. In lake sediments from North Africa and the Middle East, grain sizes change as shorelines retreat. Dust levels spike, pollen records show moisture-loving plants disappearing, replaced by species that can tolerate long, brutal dry seasons. It wasn't perfectly simultaneous everywhere. The climate never moves like a light switch. But across a huge belt of the Old World, from the eastern Mediterranean to the Indus Valley, you get the same story told in different accents. Rivers weakening, monsoons faltering, harvests failing more often than they succeed. If you'd been born into Egypt's Old Kingdom, you would have grown up believing that such things simply could not happen. For half a millennium, the Old Kingdom had been one of the most stable political systems on earth. Pharaohs of the 4th, 5th and 6th dynasties commanded thousands of labourers, organised pyramid projects on an almost absurd scale, and presided over a bureaucracy that tracked every bushel of grain. Their power rested quite literally on the Nile's flood. Each year, snowmelt and rain in the Ethiopian highlands swelled the river. When the flood came at just the right height, it spread a thin layer of nutrient-rich silt over the fields, recharging the soil for another growing season. Too low a flood meant famine. Too high meant destruction. Old Kingdom texts make it clear. Predicting and managing this cycle was a sacred science. Then, starting around 4.2 thousand years ago, the cycle broke. Nile flood records, later reconstructed from inscriptions and sediment, show a string of years with disastrously low inundations. Papyrus documents from slightly later speak of years of hunger, people eating each other's children, villages abandoned. Archaeologists see signs of social stress, fortifications going up, provincial elites carving out more autonomy, state projects stalling. By the end of the 6th dynasty, the centralized power of the pharaohs had splintered. The Grand Pyramid Age ended. Egypt plunged into what historians call the First Intermediate Period. A few centuries of fragmented rule, local warlords, and regional kingdoms. For a long time, that collapse was framed as purely political, weak kings, ambitious governors, maybe an internal crisis of ideology. But when you line up the timing with the paleoclimate data, a different picture emerges. The Old Kingdom seems to have hit the wall just as the Nile's reliability fell apart under broader regional drying. In Mesopotamia, the story rhymes. The Akkadian Empire, founded by Sargon of Akkad around 2330 BCE, was the world's first true territorial empire. It welded together dozens of Sumerian city-states into a single political unit stretching from the Persian Gulf deep into northern Syria. At its height, it was a machine for extracting grain and labour, funneling surplus from the countryside into royal storehouses and standing armies. Then, in the span of a few generations, that machine seized up. In northern Mesopotamia, settlement patterns show a striking contraction around the 4.2 Kiloyear mark. Dozens of villages and small towns are abandoned. Fields go fallow. In some places, soils show evidence of wind-blown dust and salt accumulation, signs of over-irrigation meeting decreasing rainfall and rising evaporation. A famous site called Tel Leilan, in what is now northeastern Syria, tells the story in layers. Under Akkadian rule, it boomed into a major administrative centre. Then, suddenly, the archaeological record shows a collapse. A thick layer of wind-blown dust blankets the ruins. For about 300 years, large-scale occupation nearly vanishes. When people return, they're farming at a much smaller scale. Cuneiform tablets from the late Akkadian and immediately post-Akkadian periods are filled with ominous phrases. The fields yielded no grain. Famine was in all lands. References to people selling children to pay for food. One text describes the great storm that devastated the region, which some researchers interpret as a metaphor for the long drought and dust storms. Did climate alone topple Akkad? Almost certainly not. Empires always crack along pre-existing fault lines, succession crises, rebellions, overextension. But the evidence suggests those cracks were widened by a prolonged, region-wide drying that undermined the basic agricultural base the empire depended on. Farther east in the Indus Valley, the pattern appears again, though the details are murkier. The Indus or Harappan civilization flourished along the river systems of what is now Pakistan and northwest India. It was remarkably sophisticated. Well-planned cities with grid layouts, advanced drainage, standardized weights, a writing system we still can't read. For centuries, it sustained large urban populations without huge palaces or obvious monuments to kings. Around 4.2 thousand years ago, things start to shift. Paleoclimate records from the Arabian Sea and nearby lakes show a weakening of the Indian summer monsoon around this time. Less monsoon rain means less reliable river flow, less recharge of groundwater, more stress on rain-fed agriculture. In the Indus region, urban centres like Mohenjo-Daro and Harappa begin a slow decline. Construction quality drops. Public works are neglected. Populations seem to disperse towards smaller settlements to the east, probably chasing more dependable rainfall. There's no single dramatic destruction layer, no invading army leaving inscriptions boasting of conquest. Instead, it looks like a long, complicated unwinding, political, economic, and ecological, playing out against the backdrop of a climate system that had shifted into a drier gear. What makes the 4.2 Kiloyear event so eerie is how many of these stories line up in time. Old Kingdom Egypt falters. The Akkadian Empire implodes. Urban Indus centres retract. In the Levant and Anatolia, other cultures show signs of reorganisation and stress. In parts of China, early dynastic societies confront their own hydrological surprises. Different languages, gods, and political systems, all hit by versions of the same basic problem. The water they'd built their world around wasn't behaving the way their grandparents promised it would. Not every region suffered equally, and not every collapse can be pinned neatly on climate. But the synchronicity is hard to ignore. From multiple independent climate archives, the mud at the bottom of lakes, the chemistry of cave drips, the dust trapped in distant ice, we see a broad band of drying roughly centred on 4.2 thousand years ago. From archaeology and ancient texts, we see some of the world's first great states buckling under unusual environmental stress at the same time. In the framework of Gerard Bond's 1,500-year rhythm, this begins to look less like coincidence and more like a scheduled stress test. After the Younger Dryas reset near the start of the Holocene, a few thousand years of relatively stable warmth allowed agriculture to spread and complex societies to take root. Then, roughly 3,000 to 4,000 years later, the system hiccuped. Not an ice age plunge this time, but a persistent drying that targeted exactly the regions where early civilization had clustered. The result wasn't human extinction, it was reorganization, empires shrinking or vanishing, populations moving, technologies and social systems adapting under pressure. But it left a mark deep enough that later Egyptians would remember a time when the river of Egypt was empty, and Mesopotamian myths would speak of ages when the gods withdrew the rains. And in the sediments and stalagmites the planet kept time, quietly ticking toward the next reset, one that would arrive more than 1,000 years later, just as a new set of Bronze Age kingdoms were reaching their peaks. By the late 2nd millennium BCE, it looked like the Eastern Mediterranean had figured civilization out. From Greece to Egypt to Mesopotamia, a chain of kingdoms and city-states hummed along the coasts and river valleys. The Hittite Empire dominated Anatolia from its fortress capital at Hattusa. Mycenaean palace-states ruled the Aegean from citadels like Mycenae, Pylos and Tiryns. In the Levant, wealthy ports like Ugarit and Byblos sat at the hubs of trade routes that stretched from the Italian peninsula to the mountains of Iran. Egypt's new kingdom projected power deep into Canaan and up the Nile. They were separate states, speaking different languages, worshipping different gods. But they were bound together by something new in human history, a dense international system of trade and diplomacy. Clay tablets from this period read almost like emails. Kings address each other as brother, complain about delayed shipments of copper, ask for more timber, more horses, more gold. Shipwrecks like the Uluburun off the coast of Turkey show what this network meant in practice. A single vessel loaded with copper ingots from Cyprus, tin from the east, glass ingots, ivory, exotic woods, luxury goods. The Bronze Age world ran on these flows of metal, grain and information. Then, around 1200 BCE, that world fell apart with shocking speed. Across a few decades, palace complexes burn. City walls are breached and not rebuilt. Writing systems disappear from entire regions. The Hittite Empire vanishes from history. Mycenaean Greece retreats into centuries of poverty and illiteracy, we now call a Dark Age. For a long time, historians tried to find the one big cause. Maybe it was new iron weapons. Maybe it was internal revolt. Maybe it was some mysterious invading army that burst out of nowhere and smashed everything in its path. On Egyptian temple walls, We meet the most famous candidate, the Sea Peoples. In reliefs at Medinet Habu, Pharaoh Ramesses III boasts of defeating a coalition of foreign enemies arriving from the midst of the sea. The carvings show strange ships, warriors with feathered headdresses, ox carts piled with belongings and children. The texts describe them as a people whose countries were destroyed, now seeking new lands to settle. For centuries, this was taken at face value, a simple story of invasion. A wave of destructive migrants hits the coastlines. Cities fall. The end. But the more we learn about the climate of the Late Bronze Age, the more that picture looks incomplete. Across the eastern Mediterranean, independent lines of evidence point to a prolonged period of drought and food stress, right around the time everything unravels. In cores from the Sea of Galilee and lakes in Turkey and Cyprus, sediment chemistry and pollen records show a shift toward drier conditions, with fewer trees and more drought-tolerant plants. Speleothems from caves in Israel and Syria register changes in oxygen, isotopes, consistent with reduced rainfall. In some sequences, this dry phase lasts for a century or more. Texts from the time echo the geology. At Ugarit, tablets speak of grain shortages and desperate pleas for food aid. Egyptian records from the reign of Meneptah and Ramesses III mention years of hunger and emergency grain shipments dispatched to Canaan. In the Hittite realm, letters from provincial governors beg for grain, because we will all starve if no grain comes in this year. Imagine what that means on the ground. The Great Bronze Age states had built their power on the ability to move surplus, taking grain from farmers, storing it, and redistributing it to soldiers, craftsmen, and urban populations. As long as the harvests were good somewhere in the network, the system could smooth out local failures. A drought in one region could be patched with imports from another. Ships would carry barley and emmer instead of copper and tin that season. But what happens when the drought isn't local? If winter rains falter across much of the eastern Mediterranean at once, if several harvest regions take repeated hits in the same decade, the whole buffer system starts to fail. Everybody needs food at the same time. Nobody has enough to spare. Under those conditions, the same interdependence that once made the Bronze Age so resilient becomes a liability. Trade routes that normally move luxury goods turn into lifelines for grain, and then targets. Pirates and raiders appear. City-states that were partners in good years become rivals in bad ones. This is where the Sea Peoples start to look less like a mystery army materializing out of nowhere, and more like the mobile edge of a much larger social and ecological crisis. If multi-year droughts hit the Aegean, Anatolia and the Levant, coastal and island societies that relied on imported grain would be among the first to feel the crunch. Famine pushes people to move. Groups that had lived as marginal farmers, pastoralists or small-scale traders might band together, outfit ships, and head toward the only places that still seem to have food, the rich lowland kingdoms like Egypt. What Ramesses III records as a terrifying invasion by northern peoples could be, in climate terms, a wave of climate refugees and opportunistic raiders, people whose homelands had already been destabilized by the same environmental stress. Meanwhile, the big land empires were cracking from within. The Hittite Empire disappears so abruptly, it leaves historians with almost nothing but questions. Hattusa is burned and abandoned. Peripheral cities are destroyed. There's no clear record of a successful conqueror marching in and taking credit. One plausible scenario is that several bad harvests, combined with overtaxed subjects and external attacks, pushed the imperial system past the point of recovery. Once the central administration failed to deliver grain and protection, loyalty evaporated. Provinces peeled away, and the empire simply imploded. In Mycenaean Greece, the pattern is different but rhymes. Palace centres are burned, their archives written in the Linear B script stop. Population drops. Trade with the wider eastern Mediterranean collapses. For centuries afterward, Greek communities live smaller, poorer, more locally focused lives. The old networks that brought in metals and luxury goods are gone, and with them the economic basis for palace bureaucracies and warrior elites. Archaeologists see similar fractures up and down the Levantine coast. Some cities are destroyed and never rebuilt, others shrink behind hastily strengthened walls. In Cyprus, copper production dips. In the broader Near East, long-distance trade in tin, a critical component of bronze, breaks down. Without tin, bronze weapons and tools become harder to produce. Iron begins to take its place, but in these first centuries it's not yet a reliable, mass-produced substitute. Climate stress didn't act in a vacuum. There were surely palace coups, succession crises, external enemies eager to exploit weakness. But the timing is hard to ignore. A web of drought, famine, migration and war seems to have tugged at every strand of the late Bronze Age system at once, until the whole thing tore. In Bond's timeline, this catastrophe doesn't stand alone. It lands roughly 3,000 years after the end of the Younger Dryas, and about 12 to 1,300 years after the 4.2 Kiloyear event that helped kneecap the Old Kingdom and Akkad. Not a metronome perfect 1,500 years, but close enough that many paleoclimatologists see it as another beat in the same long rhythm, a period when ocean-atmosphere patterns once again shifted into a mode that brought unusual region-wide stress to the very places that had grown most dependent on climate stability. The result, again, was not the end of humanity. It was another forced reorganization. Phoenician city-states would rise from the rubble of Levantine ports. New peoples speaking early forms of Aramaic and Hebrew would appear in the highlands. In Greece, the memory of palace kingdoms would survive only as myths of heroes and wars, stories later written down as the Iliad and Odyssey. But for the people who lived through it, the message would have felt brutally simple. The sea could no longer be counted on to bring grain. The sky could no longer be trusted to bring rain, and the great names of their age, the Hittites, the Mycenaean kings, the merchant princes of Ugarit, could not protect them when the climate's hidden clock struck again. And just as the system was slowly stitching itself back together under new rules, another civilization was about to find out what it meant when that clock tilted the other way, not toward drought, but toward a brief and unusual warmth that would help build one of the most famous empires in history. When Rome first appears in the historical record, it's a nobody. A small town on the Tiber, one tribal city among many in central Italy. No one looking at it in, say, the 700s or 600s BCE would have bet on it to rule the Mediterranean. The Greeks had older cities, richer temples, better navies. The Carthaginians controlled the trade routes. The Eastern monarchies had 1,000-year head starts. But Rome shows up at a very particular moment in Earth's climate story. Roughly from the last centuries BCE into the first 2 centuries CE, large parts of the northern hemisphere slip into what climatologists often call the Roman warm period, or Roman climate optimum. It's not tropical heat. It's not some blazing global spike. Think instead of a gentle nudge, slightly warmer average temperatures, especially in higher latitudes, and, crucially for the Mediterranean, relatively stable, predictable seasons. Tree rings from Central Europe widen in these centuries, signalling longer growing seasons and fewer severe cold snaps. Pollen records from around the Mediterranean show extensive cultivation of olives, grapes and grains. Alpine glaciers retreat compared to earlier and later periods, suggesting warmer summers and less persistent snow. In Greenland ice, the chemistry hints at a somewhat different pattern of storm tracks and ocean currents then in the cooler centuries that follow, into that window of relative warmth and stability, Rome expands. For a pre-industrial agrarian society, climate is destiny, more than ideology is. War, law, engineering, all of it rests on the same base: calories. And during Rome's ascent, the Mediterranean climate makes those calories easier to come by. Stable warmth means winter wheat actually makes it through the cold months instead of dying in a late frost. It means grapevines and olive trees can be planted farther north and higher up slopes than before, opening new marginal lands to profitable cultivation. It means spring rains and summer droughts follow a pattern often enough that farmers can plan instead of gamble. The result is surplus. Roman authors brag about it without realizing they're giving us climate data. Pliny the Elder lists regions of Italy where olives and vines, once rare, now thrive. Strabo describes Gaul as a land capable of heavy grain production, something that becomes literally true as legionaries clear forests and warmer conditions lengthen the growing season. Across the empire, amphorae stamped with production marks pile up in shipwrecks and ports, evidence of bulk shipments of grain, wine and olive oil moving on a scale earlier centuries never saw. That food surplus doesn't stay on the farm. It flows to cities feeding populations that climb to levels unmatched again in Europe for over 1,000 years. Rome itself may have housed upwards of 1 million people at its peak. Alexandria, Antioch, Carthage, each a giant urban organism that could only exist if hundreds of thousands of farmers, scattered across provinces, could reliably produce more than they themselves needed. Surplus also feeds the legions. A Roman army is a climate-powered machine, 20 or 30 legions plus auxiliaries, each with thousands of mouths that have to be fed every day, marching along roads, garrisoning frontiers, wintering in cold provinces. In a warmer, more predictable climate, harvest failures still happen, but less often, and rarely in every province at once. The empire can shuffle grain from Sicily to Rome, from Egypt to Syria, from North Africa to the Rhine, smoothing out local shortfalls. This is where climate and concrete meet. Stable conditions make long-term projects thinkable. You don't sink decades into building aqueducts, roads, harbours and frontier walls unless you're reasonably confident the countryside will keep supporting the work crews and the garrisons that guard them. Under the Roman warm period, that gamble pays off. Aqueducts carry water to cities that no longer depend solely on local springs. Irrigation canals and drainage works tame marshes and floodplains, converting them into new farmland. Roads knit the empire into a single logistical web, so a bumper crop in one valley can end up as soldiers' rations thousands of miles away. Even at the edges of the empire, the climate bonus shows. In Britain and along the Rhine and Danube, archaeological layers from the 1st and 2nd centuries CE hold evidence of vineyards, fruit orchards, and villa estates that push surprisingly far north. Later, during colder centuries, many of these same regions contract agriculturally. Crops that had once been viable become marginal or disappear. But climate isn't a magic wand, and historians are careful here. Rome doesn't rise just because the weather is nice. It rises because of institutions and culture that can take advantage of that nice weather. A ruthlessly effective military, flexible citizenship laws, a willingness to absorb and repurpose conquered elites, a legal framework that can support contracts and trade over long distances. Plenty of other societies have enjoyed favourable climates and never built global-scale empires. Climate is an amplifier, not an author. It takes the things a civilization is already doing and makes them easier or harder. And even during Rome's optimum, the system isn't perfectly smooth. Grain riots in Rome, famines in parts of Asia Minor and Egypt, occasional mentions of failed harvests in the sources. These still show up. The difference is that for a while the empire has the slack to cope. Then, slowly, that slack begins to shrink. By the late 2nd and into the 3rd century CE, the climate record starts to show signs of change. In some tree ring chronologies from the Alps and the Near East, growth becomes more variable. There are more abrupt, narrow years, suggesting harsher winters or late frosts. Evidence from speleothems and lake sediments hints at shifts in rainfall patterns. The old pattern of stable warmth and relatively reliable seasons starts to wobble. In the written sources, you can feel the system straining. The 2nd century ends with outbreaks of plague. The 3rd century is a carousel of short-lived emperors, civil wars and frontier crises. Some of that is politics, some is disease, but underpinning it, there are hints that the easy agricultural abundance of the earlier imperial centuries is no longer guaranteed in the same way. Again, causality is messy. Historians argue, and will keep arguing, about how much weight to give climate in Rome's story. Was the Roman warm period a decisive factor, or just a helpful tailwind? Was the later cooling a primary driver of crisis, or more like a stress multiplier added to existing problems of overextension, inequality, and governance? What's hard to ignore, though, is the timing. Rome's extraordinary phase of expansion and consolidation overlaps with one of the most stable, favourable climate windows of the last few thousand years in its core territories. Its later troubles and eventual fragmentation unfold as that window closes and new, less predictable patterns take hold. In Bond's 1,000-year rhythm, the Roman warm period looks like the crest of a long wave, a rare alignment when oceans and atmosphere settle into a mode that rewards the kind of intensive, centralized, grain-based empire Rome becomes. And just beyond that crest, as the climate's hidden clock ticks toward another shift, the conditions that once helped Rome knit the known world together begin, quietly, to unspool. The rivers still flow, the roads still stand, but the environmental foundation under them is starting to move. The empire will feel that movement first at its margins, then in its heartland, as cooler, more erratic centuries usher in migrations, crop failures and new diseases. The climate that built an empire is about to become the climate that tests and ultimately breaks it. The first real hints of that break show up where Rome touches the outside world, along the northern frontiers. Beyond the Rhine and Danube, the people Romans lazily call barbarians are living through their own version of climate change. Pollen records and lake sediments from Central and Northern Europe suggest that, between the 3rd and 5th centuries, conditions there become cooler and often wetter. Tree rings in parts of Scandinavia and the Baltic show more frequent cold snaps and shorter growing seasons. Nothing like an instant ice age, more like a series of bad hands dealt more often. For subsistence farmers in marginal climates, that matters. If you're a Germanic community, scratching out grain on the edge of what's climatically possible, just a small drop in temperature or a few badly timed frosts can turn a barely adequate harvest into a failure. Pastures shorten, fodder runs low, winters bite harder. Maybe one bad year you can ride out. String a few together, and suddenly you're choosing between starvation, raiding your neighbours, or moving. Archaeology shows that in these very centuries, many Germanic groups start consolidating into larger confederations: Goths, Vandals, Franks, Alemanni. Part of that is political evolution. Part may be a response to environmental pressure. When the land is reliable, small, scattered villages can survive on their own. When it's not, you need allies, muscle and flexibility. Look farther east and the pattern might be even sharper. Across the steppe belt of Central Asia, tree rings and lake cores hint at shifts toward colder, sometimes drier conditions in late antiquity. The timing overlaps with the apparent westward movement of nomadic and semi-nomadic groups. The Huns don't leave climate diaries, but they do appear in Roman and Chinese sources right around the period when the steppe seems less forgiving. One plausible scenario goes like this. A combination of cooler temperatures and shifting rainfall undermines traditional grazing regimes in parts of Central Asia. Horse herds need wide, seasonally predictable pastures. If those pastures shrink or change timing, mobile societies are forced to adjust their migration routes, fight harder for the best grasslands, or push into new territories. Push is exactly what Rome feels. By the late 4th century, the Huns are pressing into the Pontic steppe, dislodging Gothic groups who had been living for generations along the Roman frontier. Those Goths, already dealing with their own agricultural stress, now face mounted raiders they can't easily resist. The safest place suddenly looks like inside the empire. In 376, tens of thousands of Goths appear on the Danube, begging to cross into Roman territory as refugees and federate allies. Roman administrators mishandle the crisis. Corruption, exploitation and hunger turn would be subject into rebels. 2 years later, at Adrianople, a Roman field army is destroyed. Climate didn't plan that battle, but the chain, cooler, shakier harvests, pressure on steppe ecosystems, cascading migrations, overloaded Roman diplomacy, fits a pattern we've already seen at earlier climate turning points. Environmental stress nudging human systems toward their fracture lines. Inside the empire, the fields are also less forgiving than they used to be. In parts of Gaul, the Alps and the Balkans, late Roman and early medieval tree rings show more frequent severe years, sudden narrow growth rings that point to harsh winters or damaging late frosts. Lake sediments and cave deposits suggest that Mediterranean rainfall patterns become more erratic. Periodic droughts hit North Africa and the Near East, regions that had become Rome's grain superpowers. When those breadbaskets stumble, everything else wobbles. Late Roman texts start to mention famines, not as once-in-a-century disasters, but as recurring features of life in some provinces. Coin hoards and abandoned villas point to economic contraction in rural areas. Tax burdens rise as the state tries to squeeze enough revenue out of a less predictable surplus to pay soldiers and bureaucrats. If you're a small landowner and your harvest fails, you still owe the tax. Do that a few times in a row and you end up selling your land to a big estate just to survive, or binding yourself to a powerful patron for protection. The social pyramid that had already been steep under the High Empire becomes even sharper, with a narrow elite and a mass of people trapped in debt and dependence. Here's where climate acts less like a hammer and more like a weight placed on every weak point in the system. Political instability. Cooler, erratic years make it harder to guarantee grain to the capital and pay to the troops. So emperors bid for loyalty with extravagant donatives and tax breaks, hollowing out the fiscal base. Military pressure. A few bad seasons in the north or on the steppe translate into more raiding, more refugees, more crises along frontiers that are already expensive to defend. Social inequality, crop failures and market shocks push marginal farmers into the arms of big landlords, undermining the old civic institutions Rome relies on. None of this means climate killed Rome in some simple deterministic way. Internal rot, corruption, succession chaos, overextension, the tension between rich core and poorer periphery would have been dangerous under any weather. But the emerging picture from ice cores, tree rings and sediments suggests that Rome's last centuries in the West played out not on the same stable stage as its rise, but under a flickering, less generous sky. As the Western Empire fragments in the 5th century, the world around it is literally cooling into a new regime. Boundaries that once separated Romans from barbarians blur as climate-stressed migrants settle inside imperial borders and carve out new kingdoms on former Roman soil. And just as this long, uneven cooling trend is reshaping the map of Europe, something even stranger is about to happen to the climate itself. A sudden, mysterious darkening that people at the time describe in one chilling phrase. The sun stopped giving its light. In 536, people all across the old world start saying the same unnerving thing. The sun looks wrong. A Byzantine historian, Procopius, writes that, during this year, a most dread portent took place. For the sun gave forth its light without brightness. It seemed exceedingly like the sun in eclipse, for the beams it shed were not clear. Another writer in the eastern Mediterranean notes that for nearly a year and a half, the sun was so dim it gave only a feeble shadow. In Italy, Cassiodorus complains that the usual bright sky has turned bluish, that no true warmth reaches the earth. Chinese chronicles mention yellow dust like fog in the sky and summer frosts. Irish annals talk about a failure of bread beginning in 536. Across Eurasia from Constantinople to Chang'an, people begin recording strange cold summers, weak sunlight, and harvests that simply don't come in. They don't know it, but they're living under a global mystery cloud. Whatever happened in 536 wasn't just a bad regional season. Tree rings from Scandinavia to the Alps, from North America to Siberia, suddenly narrow. That means radically slower growth, colder temperatures, shorter growing seasons. In some high-latitude trees, the rings for 536 and 537 are among the thinnest in 2,000 years. The ice tells the same story, but with more detail. Deep cores drilled from Greenland and Antarctica preserve annual layers of snowfall like pages in a frozen book. In layers dated to the mid-530s, scientists find huge spikes of volcanic sulfate, chemical fingerprints of massive eruptions that injected sulfur into the stratosphere. Those droplets of sulfuric acid act like tiny mirrors, scattering sunlight back into space, dimming and cooling the planet. For a long time, nobody knew exactly which volcanoes were to blame. The written sources are vague, but over the last couple of decades, the forensic work has sharpened. Some ice cores and ash traces point to a colossal eruption, probably in the northern hemisphere. Candidates include volcanoes in Iceland or North America, around 535 or 536. Then, just a few years later, another big eruption, this time likely in the tropics. Stack the two together, and you don't just get one bad year. You get a decade where the climate system is kicked hard and then kicked again before it recovers. Climatologists now talk about the late antique Little Ice Age, a roughly century-long cool period starting in the 530s. It's not uniform everywhere, and it's not constant, but on average temperatures in many parts of the northern hemisphere dip by up to a degree or more. That may not sound like much. For agrarian societies already living close to the edge, it's deadly. Imagine you're a peasant in Gaul, or a farmer in Anatolia, or a smallholder on the Yangtze plain. Spring comes later, summer never really warms up, rains fall at the wrong time. The grain heads don't fill properly, the fruit doesn't ripen. You harvest what you can, but the barns don't look like they should. Maybe you make it through that winter by eating seed grain, by selling tools, by cutting down on everything. Then the next year is just as bad, or worse. Historical records from the 53s and 5040s start to fill with references to famine, crop failure, and desperate measures. In parts of the Eastern Roman Empire, imperial edicts discuss remitting taxes, relocating people, feeding the poor. In Northern Europe, archaeology shows abandoned farms and changes in settlement patterns. In China, some local records mention starvation and people selling children to survive. It's not that 536 creates crisis where none existed. The post-Roman West is already fragmented. The Eastern Empire is fighting expensive wars. The Sasanian Persians are a constant rival. But the mystery cloud acts like a sudden, brutal stress test. Food systems crack first. When harvests repeatedly fail, prices spike, hoarding increases, banditry rises. Grain importing cities become fragile. Armies which rely on requisitioned or taxed surplus are harder to maintain. Peripheral regions that used to be barely manageable become ungovernable. Local strongmen, bishops, warlords step in where imperial structures falter. Later chroniclers look back and single out 536, and the following years as among the worst times anyone could remember. Modern historians have half-jokingly called 536 the worst year in history to be alive. That's a bold label, and obviously you can't put a single date on all human misery, but the combination we see in the evidence is brutal. An abrupt, global-scale dimming of the sun, multi-year harvest failures across continents, rapidly dropping temperatures, and, soon after, the arrival of something even more devastating. The first pandemic of bubonic plague in recorded history. We'll come back to that plague in the next section. What matters for our bigger story is this. The 530's cooling is not just a random blip. When you overlay the ice core record of volcanic sulfate on the longer pattern of Bond events and climate swings, it sits right at a major downturn in the 1,500-year rhythm. Younger Dryas, 4.2 Kiloyear drought, late bronze collapse. Roman cooling. Now, in late antiquity, another sharp sudden shove from the climate system, this time literally arriving out of a clear blue sky. Each time, the mechanism is a little different. Sometimes it's gradual changes in ocean circulation, sometimes shifts in solar output, sometimes a volcano or two or three, going off at exactly the wrong moment. But again and again, when the background climate cycle is heading toward a cooler, less stable phase, it seems unusually easy for a single shock to tip whole regions into crisis. In 536, that shock took the form of a mystery cloud that made the sun itself look sick, and in its shadow famine, fear, and disease began to spread, ushering in a century many later writers would simply call the Dark Ages. The disease doesn't start in Constantinople. Like almost every pandemic in history, it begins out on the fringes, where human trade routes intersect with animal ecologies we barely understand. Somewhere in Central Asia, or maybe along the East African coast, a bacterium that usually lives quietly in rodent populations finds a new pathway. Today we call it Yersinia pestis. To the people who first met it in the 5040s, it had no name. It was just terror. We can trace its arrival the same way we trace the mystery cloud, by stitching together fragments. Procopius again, writing about a new disaster that struck all mankind, starting in Egypt and moving from port to port until it reached the capital. Other chroniclers describe ships bringing grain up from Alexandria, and with it, stowaways, black rats and their fleas, carrying an invisible killer. In 541 or 542, after years of cold summers, poor harvests and social strain, the plague hits Constantinople. The descriptions are almost surreal, bodies piling up in streets. Corpses left unburied, because there aren't enough living to move them. Officials trying to count the dead and giving up. Some accounts, probably exaggerated, talk about 10,000 people dying in a single day. Even if the real number is smaller, the pattern is clear. This is a mortality event on a scale nobody in the Mediterranean world has seen before. Modern genetic work has pulled fragments of plague DNA from skeletons dated to this period. They match Yersinia pestis. This is the same basic pathogen that will come back in the 14th century as the Black Death. Different strain, same family. And the timing is brutal. Climate doesn't cause plague, but it changes the playing field. Those years of strange skies and failed crops, didn't just make people hungry. They made them vulnerable. When you're undernourished, your immune system tanks. When famine forces people into cities in search of grain, you get denser, more desperate populations. When governments are stretched thin trying to feed people and fight wars, basic sanitation and public health, what little existed break down. Add in disrupted ecosystems. Some researchers think climate swings in Central Asia and East Africa may have jolted rodent populations, pushing plague reservoirs closer to human trade routes. In this reading, the late antique Little Ice Age doesn't just weaken the host, it jostles the source. The result is a perfect storm. The Justinianic plague, as historians now call it, doesn't burn out quickly. It comes in waves, flaring up, receding, and then returning for more than 2 centuries. In some outbreaks, maybe only 10 or 15% of a local population dies. In others, perhaps half. Over the long run across the eastern Mediterranean and parts of Europe and the Middle East, demographic models suggest major population loss, tens of percent compared to what might have been. And this isn't happening in a vacuum. The Eastern Roman Empire, which we usually call Byzantium, is in the middle of ambitious reconquest wars, trying to win back Italy and North Africa. Armies march, fleets sail, exactly the kinds of movements that help spread plague. Then the soldiers start dying, taxpayers die, farmers die, craftsmen die, the empire's fiscal and military apparatus, already strained by volcanic winters and patchy harvests, starts to hollow out. You can see the contraction in slow motion. Major cities shrink. Some aqueducts fall out of use. Monumental building declines. Coin hoards, the piles of money people bury in times of fear, spike in the archaeological record, and then thin out as there's simply less wealth to hide. In the post-Roman West, where political structures are already fragmented, the shock lands differently but just as hard. Small kingdoms that barely manage to keep old Roman roads and towns functioning now face labour shortages, failing trade networks, and recurring epidemics. Many urban centres dwindle into fortified hilltops or vanish entirely. Literacy retreats into monasteries. Long-distance commerce, which had tentatively linked the Mediterranean to northern Europe, withers. To later observers looking back at crumbling forums, abandoned baths, and patchwork kingdoms, this whole stretch, late 6th, 7th, even 8th centuries, starts to blur into one label, the Dark Ages. That term is loaded and misleading. These centuries were not empty. People farmed, prayed, forged alliances, fought wars, composed poetry, copied books. But from the perspective of large-scale complexity, the kind of surplus and connectivity that support big cities, wide markets and empire-level administration, there is a clear sag. And if you zoom out beyond Europe and Byzantium, the picture rhymes. Chinese dynastic histories from this same broad period record their own sequence of climate and social shocks. In the late 6th and early 7th centuries, as the Sui dynasty struggles and the Tang dynasty rises, chronicles talk about freak frosts, untimely snow, floods and droughts clustered closer together than usual. Famine reports spike. So do accounts of epidemics, illnesses that sweep through weakened populations already stretched thin by tax demands, war and erratic harvests. Again, the exact diseases aren't always clear. Not all of them were plague, but the pattern is familiar. Climate instability, food stress, disease, political upheaval. The Sui collapse. The Tang seize power amid rebellion and chaos, then spend decades trying to rebuild population and productivity. Across Eurasia, you can feel a shared pulse of contraction. Fewer people, less trade, more localism, networks that had once stitched continents together, caravans across Central Asia, grain routes across the Mediterranean, administrative circuits within empires, fray or snap. New religions and ideologies, from Islam in Arabia to new Buddhist movements in China, spread through landscapes where old orders have been weakened. This is what a trough in a climate civilization cycle looks like from the inside. Nobody in 600 or 650 says, "Ah yes, we are currently in the low phase of a 1,500-year bond cycle." They just know that their grandparents talked about fuller granaries, thicker populations, more stable rulers. They know that fields have lain fallow because there aren't enough hands to work them, that forests are creeping back where vineyards used to be, that merchants come less often, and when they do, their goods are fewer and more expensive. If you overlay the climate data on these historical narratives, the alignment is striking. The volcanic 1-2 punch of the 530s kicks off a century-scale cool period. On top of that background cooling, you get periodic eruptions, local droughts and floods, a jittery, unstable climate that makes long-range planning hard. Into that world, plague moves like a match through dry brush. The combined effect is to reset the baseline. By the time the worst waves of the Justinianic plague finally subside and the late antique Little Ice Age begins to ease, the old world is different. Populations are lower, empires are smaller or gone. Power has shifted, borders have redrawn. In some regions like Western Europe, what had been the edge of a great empire has become a patchwork frontier. In others, like the Islamic world and Tang China, new powers are rising out of the wreckage. This is the long cold aftermath, not just a few bad years, but a multi-generational sag in human complexity that follows a sharp climate downturn and a pandemic edge. And in that sag, something else is beginning. Because if the 530s and the Justinianic plague mark the bottom of a curve in our 1,500-year rhythm, then somewhere on the far side of that valley, the next upswing is already quietly starting. New forests maturing, soils recovering, ocean and atmospheric patterns slowly shifting. Within a couple of centuries, the climate dial will start to turn again, nudging temperatures up, lengthening growing seasons, and opening doors for a new round of expansion. Around 800 CE, the cycle bends toward warmth, and the world's response will be dramatic. If you were living in Europe in the late 700s, you wouldn't have instruments that measured solar irradiance or graphs showing temperature anomalies. You'd have seasons, fields, rivers, and stories, and those would be starting to change. Grain that had struggled in cold, erratic summers was doing a little better. Vines were creeping farther north than anyone remembered. Alpine passes that had been choked with snow for most of the year were open a bit longer. Chroniclers in monasteries started noting unusually fine harvests, rivers running clear of ice earlier in the spring, and orchards bearing more reliably. On its own, that doesn't prove anything. Weather is noisy. A few good decades could just be luck. But when you lay these scattered human observations on top of the physical record, a pattern comes into focus. Ice cores from Greenland show a slow decline in the markers associated with volcanic cooling after the brutal spikes of the 530s and 5040s. Tree rings across northern Europe and Siberia begin to widen, a biological record of longer, less stressful growing seasons. Layers of mud in North Atlantic Ocean cores, those same kinds of records Gerard Bond would later comb through, start to show small but consistent shifts in the mix of tiny fossil shells and ice-rafted debris, the fingerprints of ocean circulation responding to a new thermal regime. Taken together, they point to the same quiet verdict. After 2 centuries of jittery cool, the Northern Hemisphere is warming. Not a sudden flip, a long, slow tilt. Climate scientists talk about this as a transition into what we now call the medieval climate anomaly, or the medieval warm period. It isn't tropical beach weather everywhere all at once. It's a broad, multi-century trend toward milder temperatures and, in many key regions, more stable growing conditions. And somewhere in that transition, roughly in the 8th to 9th centuries, you can draw a line. If the cold shock of the 530s and the long, plague-ridden aftermath mark the low point of one bond cycle, the trough of that 1,500-year rhythm, then around 800 CE is where the next wave crests out of the valley and starts climbing. Not because a calendar says so, but because that's where proxies and history begin to sync up in a new way. The ice and the trees say, warmth is returning. The chronicles say, societies are starting to act like it. You can see it on the ground in Europe first, because that's where the written sources are thickest. Think about what's happening there in the late 700s and early 800s. Out of the patchwork of post-Roman kingdoms in the Frankish world, one power is pulling ahead. Under Charlemagne and his successors, the Carolingian Empire stitches together a realm stretching from the Pyrenees to the Elbe. It isn't Rome reborn, but it's the first serious attempt at large-scale political integration in Western Europe since the fall of the Western Empire. Why then? There are lots of answers. Military strategy, religious legitimacy, institutional experimentation. But material conditions matter too. An empire is, at its core, an energy management system. To support armies, monasteries, scribes, and monumental building, you need surplus food. To move that surplus, you need navigable rivers and passable roads. To enforce rules over long distances, you need populations dense and prosperous enough to be worth taxing. Warmer, stabler weather nudges all of those levers in the right direction. Longer growing seasons mean more predictable harvests, especially in the temperate latitudes of northern France and Germany that anchor Carolingian power. Population begins cautiously to climb. Forests are pushed back as new fields are cleared. Grain and wine move along rivers that are ice-free for more of the year, linking hinterlands to royal courts and market towns. You don't see kings talking about phase shifts in North Atlantic circulation, but you do see them issuing capitularies about mill construction, bridge repair, and the regulation of markets, all downstream effects of landscapes that are once again capable of consistent surplus. And Europe is not alone. Around the same centuries, the North Atlantic starts to play host to a new kind of traveller. Scandinavian seafarers probing out along coasts and into open waters. In the Islamic world, the Abbasid Caliphate reaches its intellectual and economic peak, drawing food and wealth from a vast hinterland that, in many regions, is enjoying relatively favourable growing conditions. In Tang and then Song China, population and urbanization accelerate over the following centuries, riding their own complex mix of innovation, politics, and climate opportunity. The details differ place to place. The signal does not. Across the Northern Hemisphere, when you overlay proxy records with archaeology and texts, the late 8th and 9th centuries look like an inflection point. Less climatic whiplash, more years in a row where farmers can trust the sky. That kind of reliability doesn't erase war, injustice, or bad decisions. But it changes what's possible. It makes it feasible to risk planting new crops, settle new lands, build bigger ships. It gives rulers the confidence to invest in infrastructure that only pays off decades later. It gives monasteries the breathing room to copy books instead of just trying to survive the next failed harvest. From the perspective of the 1,500-year rhythm, this is the moment when the system stops sliding downward and starts climbing toward a new height. The last great cold-driven reset, the 6th century crash of population, connectivity, and empire, has done its work. Natural systems have re-equilibrated. Human systems are beginning to scale back up. And that new warmth is about to be weaponized. In the next stretch of our story, we'll follow some of the people who seize this climatic tailwind most aggressively the Vikings riding improved North Atlantic conditions to remake the map, and the societies in Europe and beyond that harness this medieval warming to launch centuries of expansion, innovation, and eventually overreach. When the first Viking raid hits Lindisfarne in 793, the chronicles don't mention sea surface temperatures or reduced Arctic ice cover. They talk about dragons in the sky, omens of blood, God's punishment. But beneath the theology and terror, there's a quieter story running in the background. The North Atlantic itself is becoming a little easier to cross. In the centuries before the Viking Age, the Scandinavian world is a marginal place. Short summers, long winters, soils that make you fight for every bushel of grain. People there are already good at wringing life out of rough conditions, mixing farming with herding, hunting and fishing, moving animals between mountain pastures and coastal meadows. But even small shifts in temperature and growing season length can tilt the balance. As the 8th and 9th centuries unfold, those shifts begin to stack up in their favour. Proxy records from around the North Atlantic, tree rings in Norway, peat bogs in Ireland, marine sediments off Iceland and Greenland point to slightly warmer, slightly more stable conditions. Not beach weather, but a few extra frost-free days, a little less winter sea ice hugging the coasts, marginal lands nudged from barely viable toward worth the gamble. On land, that means more reliable barley harvests in places that used to fail 1 year in 3, hay meadows that can support a few more animals over winter, hillsides that, with enough back-breaking labour, can be cleared and brought under cultivation. At sea, it means something else entirely. The North Atlantic is shaped by interfaces between warm and cold water, ice and open ocean, fog and clear sky. For a sailor in an open boat, a narrow ring of seasonal sea ice around Iceland or along the Norwegian coast can be the difference between possible with skill and luck. And don't even try. Multiple lines of evidence suggest that in the early medieval warm period, that ring loosened. The seasonal ice edge pulled back a bit farther north. Pack ice clogged coastal routes for fewer weeks each year. Storm tracks shifted, altering prevailing winds. All of that translates into more potential sailing windows. If your people already know how to build clinker-hulled ships and read the sea by swell, birds and stars, those extra windows are invitations. Historians argue about how much of the Viking expansion is driven by climate versus politics, versus technology, versus sheer cultural momentum. No serious scholar thinks warmth alone created the Vikings. But it's hard to ignore that the age of longships and ocean probing happens to ignite, right as the North Atlantic is offering its best terms in centuries. At home in Scandinavia, those slightly kinder conditions have a double effect. On one hand, they support agricultural improvement. More predictable harvests encourage investment in permanent fields, better ploughs, larger herds. Elite families consolidate control over land and labour, building up the resources to sponsor shipbuilding and war bands. On the other hand, success creates pressure. As fields expand and yields improve, populations grow. Younger sons find that the good land is already parcelled out. Local chiefs harden hierarchies, closing off upward mobility. You get a familiar historical pattern, a society with just enough surplus to fund risk-taking, and just enough internal strain to make risk-taking attractive. Under those conditions, a longship becomes both a weapon and a safety valve. Early raids, coasts of England, Ireland and Francia, are often framed as religious violence, pagans attacking monasteries. They are that, but monasteries are also banks, concentrated stores of silver, cattle, books, slaves, to a chieftain trying to reward followers and relieve pressure at home. They look like climate-enabled opportunity. Better crops mean you can afford to have men away for a season. Milder seas mean they have a slightly better chance of coming back. As the 9th and 10th centuries unfold, the Norse push their luck farther. First along the coasts and rivers of Europe, raids becoming overwintering camps, then full-blown settlements in places like Dublin and the French Seine Valley. Then out into the open North Atlantic. Iceland sits in a zone that, in colder centuries, is hemmed in by sea ice and brutal storms. In the early medieval warm period, the window narrows but doesn't close. Saga tradition and archaeology suggest that by the late 800s and early 900s, Norwegian and Icelandic sailors are routinely making blue water crossings in open and decked ships, using islands, seabird colonies, and currents as their guidance system. They don't do this blind. They do it in a climate that, while still dangerous, gives them enough repeatable patterns to turn rumour into route. Iceland becomes more than a raid target. It becomes a settlement frontier. Its coastal lowlands scoured by glaciers and volcanism, but warmed by the North Atlantic current, offer grass for sheep and cattle, turf for houses, driftwood for building. In a world a few tenths of a degree colder on average, the ecological margin there might simply be too tight to support a long-term farming society. In the window the Vikings encounter, it's just viable enough. From Iceland, the next steps follow the same logic. Greenland's name is propaganda, but it isn't pure fiction. When Eric the Red and his followers arrive around the end of the 10th century, they find fjords where the inner valleys can support hayfields and pastures, at least in good years. The western and eastern settlements that grow there are fragile, perched near the edge of what climate will permit. But in the centuries around their founding, proxies suggest that summers are relatively mild, sea ice relatively limited. The same is true even more precariously for the Norse push into North America, what we call Vinland. Archaeological sites like Landsorg's Meadows in Newfoundland show that Norse sailors not only reached but briefly lived in the New World around the turn of the millennium. To get there, they thread through the Labrador Sea, along coasts that are extremely sensitive to small changes in ice and storminess. A modest northward retreat of pack ice and a slightly longer ice-free season along those shores could mean the difference between a once-in-a-generation fluke voyage and a route that can be sailed often enough to justify camps, timber cutting and exploration southward. Again, climate doesn't build the ships, teach the navigation, or fuel the ambition. People do that, but the warming pulse of this bond cycle opens corridors that had been effectively closed for centuries. It's also not a one-way benefit. The same conditions that help Norse sailors spread also make the lands they're raiding more productive and more worth raiding. English monasteries sitting on rich river valleys, Frankish towns at the junctions of grain trade, Irish monastic sites controlling fertile isthmuses and lake systems. As European societies take advantage of better harvests and more stable river traffic, they become more attractive targets for exactly the kind of mobile amphibious warfare that Viking bands excel at. So climate is not the cause, but it is the stage, a slightly kinder, more predictable North Atlantic that amplifies the effects of shipbuilding innovations, social tension, and political opportunity. From the perspective of the 1,500-year rhythm, the Viking Age is one of the earliest, clearest expressions of the new warm phase, flexing its muscles. The same slow thaw that lets Carolingian rulers knit together an empire on land is, at the ocean's edge, empowering people with a very different strategy: mobility, raiding, and frontier settlement. And this isn't just a Scandinavian story. In the next part, we'll zoom out from the fjords and sea lanes to look at the broader medieval warm period, how this same climatic upswing fuels centuries of expansion, urban growth, and cultural flowering across Europe, and how, as always, the gains come with new vulnerabilities baked in. By the year 900, the warmth that had helped push Norse ships across the North Atlantic isn't just a coastal or northern story anymore. It's seeping deep into the heart of Europe. If you walk through the chronicles, you don't see medieval warm period as a phrase. That's a modern label. What you see instead are hints. Monks noting vines planted in places where none had ever grown before, records of harvests so abundant that tithes are revised upward, complaints about overcrowded villages and the need to clear new land. These are the fingerprints of a climate that for a few centuries shifts the odds in favour of growth. From roughly 900 to 1300 CE, many parts of Europe experience what climate historians cautiously call a sustained period of relative warmth and stability. Not a tropical paradise just a few tenths of a degree warmer on average, winters that are a little less brutal, growing seasons that stretch just long enough to matter. But in a world where most people live within one bad harvest of famine, just enough to matter is revolutionary. The first place you really see it is in the fields. Between the 10th and 13th centuries, European agriculture explodes. Historians used to tell this as a pure technology story. Heavy ploughs biting into northern clay soils, horse collars that let draft animals pull more weight, 3-field crop rotations that keep land productive. Those innovations are real, but they land in an environment that's becoming more forgiving. A slightly longer frost-free season means winter wheat survives more reliably. Milder springs reduce late frosts that used to wipe out blossoms. Warmer summers ripen grain in regions that had been near the edge of viability. Hilltops that had been common pasture get cleared and turned into arable field. Forests are pushed back, wetlands drained, upland plateaus terraced. Archaeologists can literally map this expansion in old field systems and pollen records, tree pollen declining, cereal pollen rising, year after year. The result is simple and brutal in its math. More calories, more grain per acre, more acres under cultivation, more animals overwintered on hay, grown in meadows that used to be marginal. A surplus that doesn't just feed the same number of mouths better, it feeds more mouths, period. Europe's population responds like any biological system given more energy. It booms. Rough estimates suggest that between 1000 and 1300, the population of Western Europe may have doubled, even tripled in some regions. Villages that had a few dozen households become sprawling parishes. New settlements appear on what had been forest edge. Marginal soils, once too risky to farm, are brought into rotation because climate and technology together make them just profitable enough. That demographic surge transforms everything above the soil line. Surplus grain doesn't just feed peasants, it frees up specialists. If a village can reliably produce more food than it consumes, some of its people don't have to farm. They can become full-time blacksmiths, millers, merchants, scribes. They can move to market towns, which swell into cities. They can answer a bishop's call to build something that no one generation could ever finish. This is the background climate for one of the most visually obvious features of medieval Europe, the age of cathedrals. Between the 12th and 13th centuries, a wave of stone and glass surges across the continent. Chartres, Reims, Notre Dame in Paris, Cologne, Canterbury. These are not the projects of starving, precarious societies. They are multi-generational investments in stone, labour and faith that assume the future will be stable enough to justify starting something that your grandchildren will only just complete. To quarry, transport and raise tens of thousands of tons of stone, you need more than piety. You need scaffolding industries, literally and figuratively. You need timber for cranes and roofs, iron for tools, food to support armies of masons and carters and glaziers. You need roads and rivers safe enough to move all that material. That web of support is only possible in a Europe that is, for the moment, running an energy surplus. Urban centres ride the same tide. towns that had been little more than fortified crossroads become commercial hubs. River traffic becomes more predictable as winters soften and ice-bound months shorten. Fairs and trade routes proliferate, connecting grain belts to textile centres, salt pans to inland markets. Merchants form guilds, city councils assert charters, and stone walls rise around what used to be wooden palisades. The climate signal in all of this isn't obvious until you look at the edge cases. Take wine. Vineyards have very clear climatic limits. Grapevines need a certain amount of heat over the growing season to ripen fruit with enough sugar for wine. Shift the average temperature a little colder, and the northern boundary of viable viticulture retreats. Shift it warmer, and the line moves north. Medieval documents and place names from England and Germany are full of new vineyards during this warm phase. Grapes cultivated in southern England, in parts of the Rhineland and Central Europe, that today are on the chilly margin for quality wine, if they manage at all. Monasteries in these regions write about successes and failures in tending vines as if it's a new and exciting experiment. To a climate scientist, that's not just quaint history, it's a proxy. It tells us that for several centuries, warmth extended vineyards into zones where, in later centuries, they would struggle or disappear. But it's critical not to turn this into a simple, uniform picture. The phrase medieval warm period can be misleading. It suggests a global thermostat turned up evenly from Iceland to Indonesia. The evidence doesn't support that. Tree rings, lake sediments, glacier lengths, and coral records tell a more complicated story. Warming appears strong and persistent in parts of the North Atlantic region, Europe, and perhaps parts of the North Pacific. Elsewhere, the signal is weaker, patchy, or even reversed at certain times. Some areas see drier conditions instead of just nicer weather. Others remain largely unchanged within the noise of natural variability. So when we talk about Europe's golden centuries, we're really talking about a regional sweet spot within a broader, uneven climate pattern. A phase of the 1,500-year rhythm where this particular corner of the world experiences a run of luck. Temperatures, rainfall, and ocean patterns lining up in a way that amplifies human effort. From the perspective of the Bond cycle, this is the flourishing arc. Earlier in the warm phase, the Vikings used favourable seas to raid and explore. Now those same underlying climatic conditions are underwriting a different form of expansion, inward, upward, and upward again. Fields into forests, villages into towns, timber roofs into stone vaults reaching for heaven. And as always, success carries its own trap. Every cleared forest is less buffer against future fuel shortages. Every marginal hillside brought under the plough ties more people's survival to stable weather. Every new town concentrates risk in crowded, interdependent systems that handle growth far better than they handle shock. For 3 or 4 centuries the climate mostly cooperates, long enough for people to forget that it doesn't have to. In the next section, we'll step outside Europe and see how, at roughly the same time, other regions are riding, or missing, the same climatic wave, showing that this warm pulse is part of a global pattern, not just a local lucky streak. While Europe is clearing forests and raising cathedrals, the same centuries look very different elsewhere on the planet. But the timing keeps lining up in suspicious ways. Start in China. When Europe is just beginning to stumble out of the post-Roman shadows, the Tang dynasty is already running one of the most sophisticated states on Earth. From the 7th to the early 10th century, China experiences a period that many historians see as a political and cultural high point. Chang'an and Luoyang as megacities, poetry and painting flourishing, bureaucrats chosen by exam instead of birth. Behind the philosophy and porcelain, you find something more basic, stable food. Pollen records from Chinese lakes, tree rings from the Tibetan plateau, and glacier reconstructions from the high Asian ranges all point toward a stretch of relatively mild, moist conditions across large parts of East Asia from roughly the 7th through 12th centuries. Not perfectly smooth, not everywhere at once, but good enough and long enough to support intensive rice agriculture in the south and wheat and millet in the north. The Tang tax system literally counts households and fields. For centuries, those numbers trend upward. The Grand Canal ties grain-rich regions to hungry capitals, and the state can move huge surpluses to buffer local failures. That kind of hydraulic bureaucracy only works if you can mostly trust the rivers, predictable monsoons, snowmelt that behaves, floods that are disastrous some years, but not existential every decade. Then, as the Tang gives way to the Song in the 10th century, the climate signal sharpens into something even more striking. Under the northern and southern Song from the 10th to 13th centuries, Chinese agriculture takes a leap. One of the heroes of the story is a plant, fast-ripening champa rice imported from what's now Vietnam. It allows multiple harvests per year in warmer, wetter southern regions. That innovation only pays off if the warmth and rainfall cooperate. Proxy records suggest they usually do. The result is a surge in population, by some estimates from around 50-60 million in the Tang to perhaps 100 million or more under the Song. Cities like Kaifeng and Hangzhou swell into million-person metropolises, sustained by river and canal networks feeding them grain from a hinterland that, for this stretch of centuries, produces a lot more than it used to. Put Europe and China side by side on a timeline, and you get a weird mirror. While cathedrals rise along the Seine and Rhine, pagodas and city walls rise along the Yellow and Yangtze. Different technologies, different religions, different political theories. But the same basic pattern. A long, relatively stable warm phase turned into bureaucracy, art, and dense urban life. Swing southwest, and you find another centre of gravity waking up under similar skies. After the initial expansion of Islam in the 7th and 8th centuries, the Islamic world moves into what historians call the Islamic Golden Age, roughly 8th to 13th centuries. Baghdad, then later cities like Cairo and Cordoba, become intellectual and commercial hubs, connecting the Mediterranean, the Indian Ocean, and the Silk Road. Here too climate leaves fingerprints. Sediment cores from the eastern Mediterranean, stalagmites from caves in the Middle East, and Nile flood records suggest that from around the 9th to 12th centuries, large parts of the Islamic world sit in a relatively favourable hydroclimatic window, not uniformly wet, but with enough regularity in rainfall and river flow to support irrigated agriculture on a vast scale. The Abbasid caliphs can tax grain from the Tigris-Euphrates basin, date palms from irrigated oases, and crops pulled from complex canal systems stretching across Mesopotamia and Persia. In Egypt, reasonably reliable Nile floods mean predictable harvests, which means the state can plan. You don't build observatories, libraries, and hospitals across 3 continents if you're constantly one step from famine. The intellectual explosion, algebra, optics, medical encyclopedias, translations of Greek philosophy, is powered by merchants moving along trade routes that depend on more than just security. They depend on winds and water. Monsoon patterns in the Indian Ocean during this warm phase appear relatively stable, giving sailors a dependable seasonal rhythm. Ride the southwest monsoon toward India and East Africa. Catch the northeast monsoon home. That predictability underwrites the commerce that underwrites the scholarship. Meanwhile, on a very different continent, in a very different technological world, the pattern shows up again. In the river valleys of what is now the central United States, around 1000 CE, the Mississippian culture begins to crystallize. By the 11th and 12th centuries, a city we now call Cahokia rises near present-day St. Louis. Huge earthen mounds, plazas, wooden palisades, surrounding a population that may have reached tens of thousands. Cahokia doesn't have writing, stone cathedrals, or iron ploughs. But it has something just as telling. Maize, pollen and charcoal records from the Mississippi floodplain show an uptick in cultivated plants and land clearance starting around this same warm window. Tree ring data from the region suggest a run of years and decades with generally favourable moisture and growing season warmth, punctuated by droughts, but clement enough overall to support intensifying agriculture. That agricultural base allows social stratification, long-distance trade in shells, copper and exotic stones, and monumental construction. You don't move that much earth with buskets and digging sticks, unless you're very sure that someone else is going to grow enough food to keep you alive while you do it. And then, out on the world's largest ocean, another kind of expansion is underway. Between roughly 900 and 1300, Polynesian navigators pushed their canoes into almost every habitable island in the central and eastern Pacific. Hawaii, Rapa Nui, Aotearoa, New Zealand, all are settled within this broad window. Exactly why the burst happens then is still debated, but climate likely plays a role. Reconstructed sea surface temperatures and wind patterns suggest that parts of the Pacific during this period see conditions that would have made certain routes more accessible. Altered positions of the intertropical convergence zone, slightly shifted trade winds and sequences of El Niño-like events. For master navigators reading stars, swells and clouds, subtle changes in prevailing winds can mean the difference between a voyage that's barely possible and one that's reliably repeatable. Combine favourable wind and current regimes with stable enough conditions on already settled islands to generate population pressure, and you get an outward push. Each new island chain becomes another node in a vast, low-tech, high-skill network spread across millions of square kilometres of ocean. Put all of this together, Tang and Song China, the Islamic Golden Age, Cahokia, Polynesian voyaging, and a pattern starts to emerge. We're not looking at a single global empire broadcasting technology around the world. These cultures have almost no direct contact with each other. Yet between about 900 and 1300, you see a clustering of expansions, urbanizations and cultural flowerings, each tuned to local circumstances but sharing a hidden common denominator. A few centuries where the climate dice in many regions are rolling more sixes than ones. That doesn't mean every warm year is good or every drought is absent. Local disasters still happen, states still fall for political and military reasons. But when you zoom out, the timing of these surges lines up suspiciously well with the same warm pulse that's greening European hillsides and filling cathedral treasuries. This is what a global rhythm looks like from the ground. Not a uniform soundtrack, but different civilizations improvising in the same key at the same time, because the underlying beat, the ocean currents, the wind belts, the long solar cycles, is giving them all a little extra room to move. And as in Europe, that extra room is being used to build systems that assume tomorrow will look a lot like today. In the next section, we'll watch what happens when that assumption sails to the edge of the map, into a marginal colony at the cold fringe of this warm phase, where a few degrees of cooling and a shift in sea ice can turn a fragile success story into silence. When the Vikings looked west from Iceland in the late 10th century, they weren't staring into a frozen wasteland. They were looking into the edge of a warm phase. Around the year 985, Eric the Red sails from Iceland with a few hundred people and livestock, chasing rumours and exile. What he finds along the southwestern coast of Greenland is, by Arctic standards, surprisingly forgiving, sheltered fjords, summer meadows, patches of soil that can be coaxed into production, sea lanes that, during many summers, are open enough for wooden ships to slip through. That's the key. The medieval warm period doesn't turn Greenland into Denmark. It just nudges the climate a little. slightly warmer summers, a somewhat shorter sea ice season, a longer growing season by a handful of weeks. In a continental heartland, those are marginal gains. On the edge of the Arctic, they're the difference between impossible and barely workable. The Norse try to make it work. 2 colony clusters take shape, the eastern settlement near modern Qaqortoq, and the western settlement farther north. At their peak, together they probably hold a few thousand people, tiny on a world scale, but the largest European outposts in the Western Hemisphere for centuries. And they do something counterintuitive in Greenland: they farm. Archaeology and old bones make this clear. Pollen trapped in lake sediments shows a sudden appearance of grasses and weeds associated with pasture and disturbed soils. Microscopic fragments of charcoal hint at controlled burning to clear scrub. The isotopes in sheep, goat and cow bones tell a story of animals feeding on local vegetation, not just imported fodder. Dung layers build up in old byres. This is not a temporary hunting camp. It's an agricultural landscape, wrenching calories out of the margins. The Norse diet in Greenland starts out surprisingly rich in land food. Analysis of human skeletons from early graves show carbon and nitrogen signatures, consistent with a heavy reliance on domesticated animals. Cheese, milk, meat from cows and sheep. Maybe a bit of barley if they could coax it to ripen in sheltered plots. Taken together with the ruins, stone longhouses, churches, even a cathedral, you get a picture that doesn't fit the stereotype of starving Vikings clinging to rocks. For several centuries, the eastern settlement in particular looks, by Arctic standards, prosperous. They tithe to the church, send furs, ivory and walrus rope back to Europe, and receive in return iron, wood and luxuries. They host a bishop, they hold law things, they marry, argue, trade. All of this rides on assumptions baked into their way of life: that the sea will stay open enough to bring a ship every few years, that the summers will stay just long enough to cut hay for the animals that will keep them alive through 9-month winters. Then the background rhythm shifts. By the 14th century, multiple climate proxies in the North Atlantic start to show a cooling trend. Sea ice expands. The onset of the Little Ice Age isn't a single year of catastrophe, it's a slow tightening. A few more bad summers per decade, a growing season shaved by a few crucial weeks. More frequent years when the hay doesn't quite last until the grass returns. Greenland's archaeology records the stress. In later phases of the settlements, the isotopes in human bones change. Marine signatures increase, more seals, more fish, fewer cattle. Cows, the prestige animals of Scandinavian farmers, become rarer in the bone assemblages. Tough goats and sheep dominate. The grand stone churches fall out of use while small chapels hang on. Some farm sites are abandoned, others show signs of desperate adaptation. More sod and stone in the buildings to conserve heat, more storage pits. Trade frays. European demand for walrus ivory drops as African elephant ivory becomes more accessible again. More sea ice and more storms make the sailing season shorter and riskier. Written sources get patchy, but the last known mention of a ship reaching Greenland from Norway comes in the early 1400s. After that, nothing. The Western settlement disappears first. By around 1350, it's gone. Excavations at some of these farms suggest a quiet end. No massacre layers, no clear evidence of sudden violence. Just abandonment. Floors without the detritus of continued life. Animal bones that suggest herds left untended. The eastern settlement limps on longer. There's a wedding recorded in the church annals in 1408, probably at Folsey, whose stone church still stands today. After that entry, the written record goes silent. When later expeditions arrive, they find ruins, not neighbours. Why did they vanish? There isn't a single agreed-upon murder weapon. but climate is very high on the suspect list. Colder, stormier conditions mean tougher sailing to and from Iceland and Norway, less trade, fewer chances for young people to leave or for reinforcements to arrive. Longer winters and shorter summers mean less reliable hay production, more livestock dying, and more pressure to switch to hunting seals at precisely the time when thick sea ice makes hunting more dangerous and less predictable. Add in soil erosion from centuries of grazing on fragile tundra soils, occasional plague waves hitting their trading partners in Europe, possible conflict or competition with an expanding Inuit presence better adapted to the changing conditions, and you get a system that has lost most of its buffers. What's important for our story is not that the Norse were foolish or uniquely rigid. It's that they had built a way of life tuned to a narrow climatic window, on the outer edge of where that way of life could function. When the broader 1,500-year rhythm tilted back toward cold, that window closed. From a distance, Greenland looks like a minor footnote to the medieval warm period. Up close, it's something else, a small controlled experiment in how far a society can push into a marginal climate when the dice are rolling well, and how quickly that advance can evaporate when the rolls start to go bad. Their stone churches and abandoned byres sit right at the hinge between the medieval warm centuries and the Little Ice Age that follows. In the next section, we'll zoom out again and watch that same cooling squeeze. Not just a few thousand Vikings on a remote coast, but major civilizations across the Northern Hemisphere. If you were living in Europe around the year 1300, you wouldn't have said, "Ah yes, the Little Ice Age is beginning." You would have just thought the weather was getting weird. The 1200s in much of Europe sit right at the tail end of the medieval warm period. Not a tropical paradise. This is still a pre-industrial agrarian world at the mercy of the seasons, but generally things had been workable. Growing seasons were long enough. Harvests, while variable, were usually sufficient. Populations had grown. Towns had expanded. Cathedrals crawled upward, stone by stone, funded by surplus grain and the taxes it allowed. Then, in the early 1300s, the background conditions start to slide. Tree rings from Central Europe begin to show narrower growth bands. Ice cores from Greenland record shifts in atmospheric circulation and volcanic aerosols. Glacier fronts in the Alps, which had retreated during the warmer centuries, begin to creep forward again, grinding over old moraines and swallowing high pastures. Nobody in a medieval village is reading tree ring charts. What they feel is this: more springs that are late and wet, more summers that never quite get warm, more autumns that close their grip too early, frosting grain that isn't fully ripe. The Great Famine of 1315 to 1317 is one of the first brutal signals that the system has changed. It starts, as these things often do, with rain. In 1315, much of northwestern Europe is hit by relentless, cold, soaking rains that drag on through spring and summer. Fields that should be turning gold are waterlogged. Grain rots in the ground or moulds in the ear. Hay meadows can't be cut properly. The fodder that will carry animals through the winter never materializes. Reserves had been thinning for years as population growth pressed up against the limits of medieval agriculture. There isn't a massive buffer of stored grain to fall back on. So when the harvest fails, the shock is immediate. Chroniclers start to note things they'd never bothered to mention before. People eating cats and dogs, parents abandoning children at monastery doors, travellers found dead by the roadside with grass in their mouths. Some accounts speak of cannibalism, not necessarily as a routine practice, but as the kind of desperate exception that sticks in the memory and the ink. And the weather doesn't bounce back the next year. 1316 brings more cold, more rain, more crop failures. Even in 1317, when conditions begin to improve slightly, the system is so depleted that recovery is slow. Seed grain has been eaten. Draft animals have been slaughtered. People are weakened not just by hunger but by the infections that stalk malnourished bodies. This is what a cooling trend looks like on the ground. Not instant glaciers and frozen rivers, but a sequence of years where the statistical averages tilt just enough to shave off the margin of safety. Colder winters play their part too. Reports from the 14th century describe rivers freezing more often and more solidly. Sea ice in the North Atlantic extends farther south. Harbours that had been reliably open for much of the year now choke with ice for longer stretches, tangling trade routes that carried grain from surplus regions to deficit ones. Alpine peasants watch glaciers that their grandparents remembered as distant white walls creep lower down the valleys, closer to forests and pasture. By the late 1300s and into the 1400s, records from Switzerland and Austria mention ice overrunning fields, burying chapels, even destroying entire hamlets. To them, this isn't climate data, it's the landscape itself turning hostile. All of this strains medieval societies in ways that are easy to underestimate. Agriculture in that world is a knife-edge business. Yields are low by modern standards. Most people live close to subsistence, even in decent years. So a run of bad harvests isn't just an economic problem, it's a physiological one. Children who grow up during or just after the Great Famine tend to be smaller, more stunted, more vulnerable to disease. Adults carry the scars of repeated near starvation. Immune systems that might have handled ordinary infections become brittle. The brittleness matters because the climate isn't just cooling. It's also rearranging where people and pathogens move. Colder, more erratic weather shifts, trade patterns and migration routes. Grain shortages push people into towns in search of work and relief. Crowded, undernourished urban populations sit right along the major commercial arteries that now reach from the Black Sea to the North Sea. When the Black Death arrives in the late 1340s, carried along those routes by fleas on rats in merchant ships, it does not hit a robust, well-fed, resilient population. It hits people whose bodies and social systems have already been run down by 3 decades of climatic stress. Historians still argue about how much the Great Famine directly caused the massive death toll of the plague. But it's hard to avoid the conclusion that repeated crop failures, colder, wetter conditions, and the demographic pressures of the early 1300s created a perfect set of preconditions: weaker hosts, strained local economies, frayed social safety nets. Meanwhile, the cryosphere, the frozen part of the Earth system, is clearly shifting into a new mode. Glaciers in the Alps, Scandinavia, Iceland, even parts of the Rockies and Andes show synchronous advances during this period and the centuries that follow in ice cores. Scientists can trace layers of increased dust and chemical markers that line up with these advances, suggesting reorganized wind patterns and possibly more frequent volcanic eruptions, both of which can reinforce cooling. From the perspective of the 1,500-year cycle, what we're seeing in the 1300s is the descending limb of the current oscillation. The medieval warm period was the crest, a few centuries of relatively benign conditions, especially around the North Atlantic. Now the system is rolling down the other side. Sea ice expands. Storm tracks shift. Winters lengthen. Summers become less reliable. The planet is not plunging into a full ice age, but the baseline is sliding cooler, and human societies that had expanded to fill the warm phase carrying capacity are suddenly oversized for the new climate. For the Vikings in Greenland, that meant the quiet disappearance of entire settlements at the edge of possibility. For Europe and much of the Northern Hemisphere, it meant something broader, a long, uneven squeeze that turns up the background risk of famine, disease, conflict and collapse. In the next section, we'll follow that squeeze as it propagates outward, beyond cathedrals and grain fields, to irrigation canals in Cambodia, imperial palaces in China, and other centres of power that discover, often too late, that their own golden ages were built on borrowed climate time. While Europe is grappling with failed harvests and plague, something eerily parallel is unfolding half a world away in the tropics. Take Angkor, the great capital of the Khmer Empire in what is now Cambodia. At its peak around the 12th and 13th centuries, Angkor isn't just a city, it's a hydraulic machine. Engineers there have carved an artificial landscape, reservoirs the size of small lakes, canals, spillways, dikes and rice fields, tuned to the rhythm of the monsoon. When rains arrive on schedule, and in the right amounts, the system is brilliant. Water is caught, stored, routed, and bled out into paddies over months. In a world without fossil fuels, that's how you turn seasonal torrents into year-round food, tax revenue and temple-building power. For a while the climate cooperates, but paleoclimate data from tree rings in Southeast Asia and sediment cores from the region's lakes tell a different story starting in the 1300s and especially into the 1400s. The monsoon becomes more erratic. Some years bring intense, destructive rainfall, others bring severe drought that drags on for multiple seasons. The Angkorian system was optimized for a certain pattern: big wet season, reliable refill of the reservoirs, predictable drawdown. When that pattern starts to wobble, the design itself becomes a vulnerability. In drought years, water levels in the Barre, the giant reservoirs, drop. Sediment settles where it shouldn't, farmers downstream get less irrigation, harvests shrink, and the margin for supporting armies and monumental projects narrows. Then, in the swing years, when the monsoon comes back with a vengeance, floodwaters roar through canals and spillways that were never meant for such extremes. Archaeologists have found evidence of hastily cut diversion channels, repaired embankments, and reworked infrastructure. It looks like a city frantically trying to keep up with a water system that has slipped its leash. By the late 14th and 15th centuries, inscriptions thin out. The monumental building slows, political power fragments. There are invasions and internal conflicts, yes, but those political shocks are landing on an ecological system that is already unstable. Angkor doesn't vanish overnight in a single apocalyptic storm. It fades. The royal court relocates downstream toward Phnom Penh. The great reservoirs silt in, canal banks slump. Forests creep back through what used to be meticulously maintained waterworks. From a satellite view centuries later, you can still trace the ghost of the system. Straight lines and rectangles under the trees. The bones of a civilization that pushed hydraulic engineering to its limits, and then found those limits moving under its feet. Farther north, in China, a different empire faces a different flavour of the same problem. The Ming dynasty rises in the late 1300s, in the aftermath of Mongol rule, and for a time it rides relatively favourable conditions. But by the 15th, and especially the 16th and 17th centuries, many proxy records from East Asia, tree rings, stalagmites in caves, historical harvest data, converge on a cooler, more volatile climate. This is the period that overlaps with what climatologists call the coldest core of the Little Ice Age, in northern China. That doesn't mean glaciers in your backyard. It means harsher winters, shorter growing seasons, and more frequent droughts punctuated by catastrophic floods. The Ming state is built around grain, the granaries of the North China Plain, rice from the Yangtze Basin, and the Grand Canal that links them to the political heartlands are the arteries of the system. When drought grips the north, something documents complain about again and again in the late Ming: harvests fall. When the monsoon shifts and rain dumps farther south or fails altogether, the carefully balanced tax and transport system begins to wobble. On top of this, some of the worst recorded floods of the Yellow River and other major waterways occur in this era. Floods smash dikes, drown fields, and displace millions. The state pours resources into dike repair and famine relief, but repeated shocks erode its fiscal base and credibility. As conditions worsen in the 1600s, local rebellions flare. Banditry grows. Nomadic and semi-nomadic groups on the colder, more stressed northern frontiers push southward. Internal and external pressures converge. By 1644, peasant uprisings and Manchu invasion topple the dynasty. Historians still argue about the exact weighting of climate versus corruption, mismanagement, or external threats in the Ming collapse. But what the climate record makes hard to ignore is that the late Ming is trying to govern a landscape whose hydrological behaviour, where and when it rains, how rivers run, is shifting in ways that amplify every political weakness. Across the Pacific, similar stories are unfolding in Mesoamerica. Long before this, classic Maya cities had already risen and fallen, with droughts likely playing a role in earlier crises. But during the late medieval and early modern centuries, several Mesoamerican societies face renewed climate stress. Lake sediments and cave deposits in Mexico and Central America indicate clusters of severe drought episodes in the 14th through 17th centuries. For agrarian communities depending on rain-fed maize, a multi-year drought is not an inconvenience. It's an existential threat. Historical accounts from the Aztec and later colonial periods describe years of hunger, crop failure, and social unrest tied to years without water. These weren't isolated anomalies. They overlap in timing, with the same broader cool phase that is bringing longer winters to Europe, erratic monsoons to Southeast Asia, and hard freezes more frequently to the North China Plain. Back in Europe, the squeeze that began with the Great Famine doesn't simply resolve once the Black Death has burned through. It morphs. As you move through the 1500s and 1600s, you see a pattern of repeated agricultural crises, wine harvests ruined by late frosts, rivers freezing more often, sea ice choking northern shipping lanes, rainy summers and brutal winters that punctuate the century. The so-called general crisis of the 17th century, wars, rebellions, state breakdowns from the Ottoman Empire to France and England, sits right in the middle of this climatic trough. Again, politics matters, religion matters, economics matters, but all of those conflicts are taking place in societies whose food systems and tax bases are under pressure from a background climate that has quietly turned less forgiving. What's striking in the data is not just that it's colder somewhere or wetter or drier somewhere else. It's the near simultaneity. Within a broad window of a few centuries, the late 13th to the 17th, you see glaciers advancing in the Alps and Scandinavia, sea ice expanding in the North Atlantic, weaker monsoons and mega-droughts interspersed with catastrophic floods in Asia, drought clusters in Mesoamerica, tree rings around the Northern Hemisphere narrowing in sync. Local expressions vary. Cambodia doesn't feel like Norway. Northern China's dust storms aren't the same as English rivers freezing solid. But behind the regional differences is a shared pattern, the descending side of a global climate oscillation, that once again is lowering the ceiling on what existing societies can comfortably sustain. Empires with very different cultures and technologies, Khmer, Ming, various European monarchies, Mesoamerican polities, find themselves wrestling with eerily similar themes. Water that comes at the wrong time or not at all, harvests that no longer match population expectations, infrastructures, canals, terraces, grain routes, designed for a climate that has quietly moved on. From the vantage point of the 1,500-year cycle, this is the cold phase reset doing what it always seems to do, not wiping the slate clean in a single blow, but tightening the environmental constraints until systems built in the previous warm phase fracture, adapt, or fail. In the next section, we'll step back from these case studies and look at the larger pattern, how ice cores, sediments, and solar records line up these rises and falls into a repeating rhythm, and how confident we really are that a 1,500-year clock is ticking beneath the surface of history. So let's step back and stack all of this together. You've got the Younger Dryas, that abrupt cold relapse about 12,900 years ago. Then, after things settle into the relatively stable Holocene climate, you hit the 4.2 Kiloyear event around 2200 BCE, a cluster of megadroughts and cooling that undercuts Old Kingdom Egypt, the Akkadian Empire, and settlements from the Levant to the Indus. Roughly a millennium and a half later, you're in the Late Bronze Age collapse. Around 1200 BCE, a whole web of Mediterranean and Near Eastern states, Mycenaean Greece, the Hittites, Ugarit, parts of New Kingdom Egypt, buckles under a pile-up of stresses, invasions, rebellions, and underneath it all, a pattern of droughts and famines seen in speleothems, pollen records, and sediment cores. Move forward another 1,500 years or so, and you land in the neighbourhood of the late Roman world. There's a warm phase, the Roman warm period, roughly centred on the 1st centuries BCE CE, then a swing downward as you head into the 3rd to 6th centuries, more climatic volatility, crop failures, pandemics like the plague of Justinian, and major population movements. Another few centuries, and 536 AD arrives with its mystery dust veil and sudden cooling. After that, you've got the dark, chilly centuries of the early medieval period, glaciation advances in the North Atlantic, and societies from Byzantium to the Maya facing repeated shocks. Then, near the top of the most recent warm swing, around 800 to 1200 CE, the pattern flips again, the medieval warm period. Viking expansion into the North Atlantic, population growth, and agricultural expansion in Europe and China, flourishing irrigation and temple building in Angkor, political complexity in Mesoamerica. And then the slope downward, the Little Ice Age and its cold, unstable centuries, peaking from the 14th through the 17th. Famines, plagues, dynastic crises, hydraulic systems pushed beyond their design. Lined up end to end, you start seeing a loose but persistent spacing. Every time civilization seems to hit a ceiling, whether it's palace economies around 1200 BCE or imperial systems in the 1600s, you can usually find a corresponding bend in the climate record that sits roughly a millennium and a half from the last big turn. That spacing isn't just coming from history books. It's literally frozen into the planet. Ice cores from Greenland and Antarctica show repeated, quasi-regular pulses in things like dust content, oxygen isotopes, and trapped greenhouse gas levels. When Gerard Bond and his colleagues started counting layers in North Atlantic sediment cores, they noticed something striking: layers rich in coarse debris. Rocks delivered by icebergs carving off from glaciers seem to cluster roughly every 1,500 years during the Holocene. Those Bond events line up within uncertainties with several of the big historical climate disruptions we've talked about. Not perfectly, not like marks on a ruler, but close enough that you start paying attention. Tree rings tell a similar story from a different angle. Dendrochronologists stitch together thousands of years of growth patterns from long-lived trees and preserved timbers. Some periods show widespread, synchronized narrow rings across the northern hemisphere, signatures of cooler, harsher years. Many of those clusters fall near the Bond event timings. Speleothems, mineral deposits in caves, encode rainfall and temperature shifts in their growth bands and isotopes, and they too often show multi-century swings with a familiar rhythm. Crucially, these signals weren't all discovered by the same person with the same pet theory. Different labs, different methods, different archives. Ice in Greenland, mud in the North Atlantic, stalagmites in Chinese caves, tree rings in Europe and North America, have produced independent chronologies. When researchers overlay them, peaks and troughs have an unnerving tendency to line up within a few centuries over and over. That convergence is what makes scientists take the 1,500-year idea seriously. If you saw one drought that lined up with one political collapse, you'd shrug and say, coincidence. But when glacial debris in the Atlantic isotope shifts in Greenland, drought bands in Chinese caves, and tree ring failures in Europe all point to the same general window, and that window keeps returning at roughly the same interval, that's harder to write off as random. Still, not everyone is convinced, and the skepticism matters. Some climatologists argue that the 1,500-year period is an artifact, a pattern we see because humans are very good at finding patterns, even in noise. Others point out that the spacing isn't perfectly regular, some events are early, some late, and the mechanisms that might produce such a tidy rhythm in something as messy as Earth's climate are still debated. There are alternative explanations too. Maybe what we're calling a cycle is actually the interaction of several different processes. Ocean circulation shifts like changes in the Atlantic meridional overturning circulation, volcanic clusters, solar variability, internal feedbacks in sea ice and snow cover. Put them together, and you might get something that looks like a loose 1,500-year beat without a single metronome driving it. Chronological uncertainty adds another wrinkle. Dating older events, especially before written records, comes with error bars. A peak in one proxy might be 200 years off from another, and if you're trying to measure a 1,500-year interval, those uncertainties can blur the pattern. So why do many researchers still talk about a 1,500-year cycle at all? Because when you see approximate synchronization across so many independent proxies, spread over vast distances, the statistical odds that it's pure coincidence drop. Ice cores don't care what's happening in Mesopotamia. Tree rings in Scandinavia don't know anything about Maya dynasties. Lake sediments in Africa and speleothems in China aren't conspiring to fake a rhythm. When they all tilt in the same direction at roughly the same times, and human societies happen to be stressed or transformed in those same windows, you have a strong circumstantial case that there's a real underlying climate oscillation at work, even if we're still working out exactly how it ticks. The honest bottom line is this. The 1,500-year rhythm is a powerful organizing hypothesis, not a settled law of nature. It's more like a rough drumbeat in the background of Earth's climate than a precise clock chime. Some beats are louder, some softer, some a little off time. But if the last several cycles are any guide, that drum is still beating. And if the last one really did ramp up around 800 CE, and we're only about 1,200 years past that turn, then we're living somewhere on the rising edge of whatever the next phase is going to be. To understand what might be pushing that rhythm, and how much of it could still affect us, we need to look up at the ultimate energy source for Earth's climate, the sun. When people in the 1600s looked up, they literally thought the sun had gone bad. Astronomers like Galileo and Cassini, using early telescopes, kept seeing the same unnerving thing. The dark freckles on the sun's surface that we call sunspots basically vanished. For decades, that period, roughly from 1645 to 1715, is what we now call the Maunder minimum, and if you overlay it on climate records, the timing is hard to ignore. Those same decades line up with some of the coldest, harshest years of the Little Ice Age in Europe and parts of North America. The famous frost fairs on the frozen Thames in London, many of them fall inside that window. Tree rings, glacier advances, written harvest records from Europe and Asia all tell versions of the same story. Shorter growing seasons, brutal winters, crop failures, and famines. So what was happening to the sun? Under normal conditions, the sun pulses with an approximately 11-year cycle. Sunspots increase and decrease in a rough rhythm. These spots are actually regions of intense magnetic activity, and they correlate with slightly higher solar output. More spots, paradoxically, means a slightly brighter, more energetic sun overall. The changes in total solar energy are small, on the order of 0.1% over a cycle. If you heard that in isolation, you might shrug. But that tiny variation is hitting a system that's incredibly sensitive to where and when energy arrives. Solar cycles don't just nudge the thermostat a fraction of a degree. They seem to tweak the patterns of circulation that move heat and moisture around the planet. The stratosphere warms and cools subtly with solar activity. Jet streams shift a little. Storm tracks wiggle north and south. In some regions, that's the difference between rain and drought, between a mild winter and a killing freeze. During a grand minimum like the Maunder event, the usual up and down heartbeat of the sun gets suppressed. Sunspots drop to almost zero for decades at a time. Reconstructions of solar output, using things like carbon-14 in tree rings and beryllium-10 in ice cores, suggest that the sun's energy dipped slightly but persistently in those years. That small dip, on its own, probably isn't enough to create a little ice age from scratch. But here's where it connects back to the bigger climate puzzle. By the 1600s, the climate system was already drifting cooler. Volcanic eruptions had been injecting aerosols into the stratosphere. Ice and snow cover were creeping outward in the North Atlantic. Ocean circulation may have been wobbling. In that context, a prolonged period of reduced solar output may have acted like a gentle but sustained push in the same direction the system was already leaning. Think of it like a boulder perched near the edge of a slope. Internal variability, volcanic dust, and ocean shifts shove it closer to the tipping point. A grand solar minimum doesn't need to be a massive kick. It just needs to arrive at the right moment and keep nudging. The Maunder minimum isn't the only time we see this pattern. Earlier in the Little Ice Age, around the late 1500s and early 1600s, there's another dip in solar activity called the Spura minimum. Climate proxies from that period show cooling in many of the same regions. Further back, around 1450-1550, some reconstructions suggest a weaker stretch of solar output, often labelled the Wolf minimum. Each of these intervals corresponds with some regional variation and dating uncertainty to clusters of harsh winters, failed harvests and glacier advances. Going the other direction, periods of higher solar activity often line up with relatively warm phases. The so-called medieval maximum in solar activity coincides broadly with the medieval warm period. Later, the modern maximum in the mid-20th century lines up with part of the 20th century warming trend, though in that case, greenhouse gas increases quickly dwarf any solar contribution. So is the sun the mysterious metronome behind the 1,500-year rhythm? Probably not on its own. And this is where the debate heats up. When climate modelers plug realistic solar variations into their simulations, they do see temperature responses, especially at regional scales. But the global average impact is usually modest, a few tenths of a degree. That matters, but it doesn't fully account for the magnitude of something like the Little Ice Age, or for the abruptness of events like the Younger Dryas. Some researchers argue that solar changes get amplified by internal feedbacks. Small shifts in solar output alter sea ice cover, which changes how much sunlight the planet reflects, which in turn feeds back into ocean circulation. Others look at how solar variability affects ozone in the stratosphere, which then cascades down to influence jet streams and monsoons. There are papers proposing links between cosmic rays, cloud formation and solar magnetism, though that line of research is highly contested and far from settled. On the skeptical side, many climatologists point out that when you look at the last several decades, solar activity has been flat or even slightly declining, while global temperatures have surged upward. That's a strong hint that in our current situation, greenhouse gases are dominating the signal. They also caution against over-interpreting historical correlations. Cold centuries and solar minima don't always match one-to-one, and other forcings, especially volcanoes, often coincide. The cautious consensus is this: solar variability is real, it matters, and it can help push the climate system toward warmer or cooler states, especially when other pieces are already moving in the same direction. But it's not a master switch that explains everything. Instead, you can think of solar activity as one gear in a much larger clockwork. The sun provides the energy and a gentle rhythm. The oceans, with their slow overturning currents, decide where that energy gets stored or released. Ice and snow determine how much of it bounces back into space. Greenhouse gases set the baseline insulation. Volcanic eruptions throw random wrenches into the system. When all of those line up when a grand solar minimum arrives during a period of weakening ocean circulation and expanding sea ice, you get a louder beat in the 1,500-year drum. When they're out of sync, the rhythm is softer or even skipped. So yes, the sun is part of the story. It shapes the background pulse against which civilizations rise and strain. But it's not the only player. To understand how these cycles reset societies, and to know where we stand inside the current one, we have to look not just up at the sky, but also down into the deep, slow-moving currents of the ocean. So where does that leave us? If there really is a loose 1,500-year rhythm, big disruptions around the Younger Dryas, then the 4.2 Kiloyear drought, then the late Bronze Age collapse, then the Roman crisis and the Dark Ages, then the Little Ice Age. What does the clock say about now? Let's do the simplest, almost childishly crude thing first. Take that last clear pivot point we talked about, the turnaround 800 CE, a cooling, stormier world easing into the medieval warm period, the Viking Age igniting, agricultural frontiers moving north, trade networks expanding. That shift in a lot of reconstructions looks like the start of the latest cycle. Now count forward. From roughly 800 CE to today is about 1,200 years. If the Bond cycle is real, and if it's close to 1,500 years on average, and if the last one did indeed start in the early Middle Ages, then strictly on that back of the envelope timeline, we're not at the reset yet. We're somewhere in the final few centuries before it. That doesn't mean a specific year circled in red on the calendar. Climate rhythms are messy. The past cold phases weren't perfectly spaced like the ticks of a metronome. Some came a bit early, some late, some stronger, some weaker. 1,500 years is more like the centre of a blurry band than a precise beat. But if you treat that band seriously, what you'd expect naturally over the next few centuries isn't a smooth continuation of what we just had. It's another turn of the wheel, a gradual drift toward a different state of the North Atlantic. Maybe more sea ice building up in the Arctic, maybe a subtle weakening of the great ocean conveyor that moves warm water north and cold water south. Perhaps more frequent harsh winters in some regions, more droughts in others, as the jet streams and storm tracks adjust. Not instant catastrophe, a slow but important reshaping of the background climate against which societies live. That's roughly what a natural forecast would look like, if you only knew about Milankovitch cycles, solar variability, volcanic randomness, and the familiar internal rhythms of the ocean. But here's the problem. We don't live in that world anymore. For almost every previous reset we've talked about, humans were passengers. We could adapt, move, farm differently, fight wars over resources, but we could not reach into the atmosphere and twist the thermostat. Now we can. Since the Industrial Revolution, We've been injecting greenhouse gases into the air at a rate that has no known parallel in the ice core record. The concentration of CO2 today is higher than anything seen in at least the last 800,000 years, probably longer. Methane and nitrous oxide are up as well. That extra insulation traps more heat, especially in the oceans. So when you ask, are we due for another reset? You have to ask a second question right beside it. What does a natural cycle even look like when you've slapped a giant anthropogenic forcing on top? This is where climate scientists get very cautious and very insistent about keeping two ideas separate. One, the paleoclimate evidence for multi-century to millennial scale North Atlantic rhythms is real enough to take seriously. You see recurring pulses in ice-rafted debris isotope ratios, dust layers. You see cold snaps and reorganizations that line up roughly 1,000 to 2,000 years apart. 2. The rapid warming of the last century and a half is overwhelmingly driven by human emissions, not by those slow natural cycles. Those statements are not in conflict. They're describing different pieces of the system. If you try to blame recent warming on some mysterious 1,500-year wave, you run into hard limits. The timing doesn't match. The natural cycle, if anything, would be nudging us toward very slow cooling, not rapid heating. The spatial pattern doesn't match either. Modern warming is strongest over continents and in the Arctic, just like you'd expect from greenhouse forcing, not a gentle change in ocean currents alone. And when you plug known solar and orbital variations into climate models, you simply don't get the spike we're seeing now. So the cautious way to put it is this. Yes, the long-term climate clock is still ticking in the background. No, that clock is not what's driving the sharp upward line in global temperatures on modern graphs. But clocks can still matter, even if you're adding a new, louder alarm on top. One of the biggest open questions right now is how our artificial warming might interact with those old natural rhythms, especially the deep currents of the North Atlantic. The Atlantic Meridional Overturning Circulation, or AMOC, is that slow planet-sized conveyor we talked about earlier. Warm, salty water flows north near the surface, cools, sinks, and returns south in the deep ocean. That circulation helps keep northwest Europe relatively mild, feeds into monsoon systems and stores, or releases vast amounts of heat. Fresh water is its enemy. Pour a lot of cold, fresh meltwater into the North Atlantic, from Greenland's ice, from increased Arctic river runoff, from changing precipitation patterns, and you change the density structure of the surface ocean. If the water is too fresh and light, it doesn't sink as readily. The conveyor weakens. In past resets, that kind of freshening seems to have been one of the triggers. Ice sheets melted, pulses of fresh water poured out, currents reorganized, climate patterns flipped. Today we are melting Greenland and the Arctic sea ice, but under completely different global conditions. A warming world, not a cooling one. So researchers are watching the AMOC like hawks. They're deploying moored instruments across the Atlantic, measuring temperature, salinity, and current strength from top to bottom. They're combing through past data, ship logs, tide gauges, satellite records, to reconstruct how the circulation has changed over recent decades. They're building models that try to reconcile proxy evidence from the last 10,000 years with the physics of a rapidly warming ocean. Some studies suggest the AMOC has already weakened noticeably since the mid-20th century. Others argue the signal is still buried in the noise of natural variability. There are papers pointing to early warning indicators of a potential tipping point. There are rebuttals saying those indicators are ambiguous and the uncertainties are huge. In other words, this is an active, unresolved scientific fight. No reputable researcher is saying, on Tuesday, 2093, the Gulf Stream will shut down and Europe will instantly plunge into an ice age, That's movie plot territory, not current evidence. What they are saying sounds more like this. We know from the geological record that the North Atlantic circulation can change, sometimes abruptly. We know that adding fresh water and heat to the system changes its stability. We have hints that some of those long, slow cycles are linked to exactly this part of the ocean engine. And we know that humans are now pushing that engine in ways that have no close analogue in the last several 100,000 years. So are we due for another reset? Chronologically, if you buy the 1,500-year rhythm, we're heading into the window over the next few centuries when the next big North Atlantic reorganization might naturally be more likely. Physically, we are also rewriting the rules by loading the atmosphere with greenhouse gases, melting ice, and warming the oceans from the top down. Put those together and you don't get a clean prediction. You get a question mark. Maybe the human-driven warming overwhelms the old cycle, smoothing it out, turning a would-be cold phase into a slightly less warm plateau. Maybe it does the opposite, pushing the system closer to thresholds where currents jump to new modes, making the eventual reset sharper. Maybe the natural rhythm gets delayed, or shows up in a different pattern than anything we've seen before. Right now, nobody can say with high confidence exactly how that interplay will unfold. What the history does give us is context. It reminds us that the normal climate of the last few hundred years was already a moving target, that civilizations have repeatedly been caught off guard when the background conditions they took for granted shifted, and that the deep ocean, not just the air above our heads, is where some of the biggest decisions about our future are being made. In the final part of this story, we'll step back from the ice cores and the ocean currents and ask the more human questions. If we really are living inside a long cycle, while also accelerating our own experiment on top of it, what can we learn from the societies that faced earlier turns of the wheel? And what might resilience look like when the next reset, whatever form it takes, finally arrives? When you zoom out over the last 10,000 years, you start to notice something uncomfortable. Climate doesn't just cause collapse or cause success. It acts more like a stress test, same kind of shock, very different outcomes. Take the 4.2 Kiloyear drought we talked about earlier in Mesopotamia and the eastern Mediterranean. Rainfall crashed. Rivers shrank. Crop failures piled up. The Akkadian Empire, one of the first true territorial states in history, crumbled. But not everyone in that broader region vanished. In the Nile Valley, Old Kingdom Egypt went through its own crisis, famine, political fragmentation, what later texts remembered as a time when the river is blood and men shrink from drinking. Yet Egypt didn't disappear. It reorganized. Provincial elites gained power. Local networks stepped in where the central state faltered. Irrigation patterns shifted. After a period of chaos, a new political order emerged. Same drought band, roughly the same timing. One imperial system shatters. Another bends, frays, and then restitches itself. Or look at the late Bronze Age collapse. From Greece to Anatolia to the Levant, palace economies imploded. The finely tuned trade machine that had moved copper from Cyprus, tin from as far as Central Asia, grain from Egypt, luxury goods everywhere, it seized up. Earthquakes, invasions, internal rebellions, and in many reconstructions climate stress and drought all piled on. The great hubs Mycenae, Ugarit, Hattusa failed the stress test. But Egypt again is interesting. It was hammered. It lost territory, fought off invaders, saw its own internal crises. Yet the Nile system, that mix of flood-based agriculture and dense local administration, limped through. Egypt was never quite the same again, but it remained a recognizable state, while neighbours dissolved into post-palatial dark ages. Why patterns repeat? Societies that handled climate shocks best tended to share a few traits. First, flexible food systems. If your entire agriculture is tuned to one narrow pattern, one rain season, one main crop, one river that always behaves a certain way, you're efficient in the good years and brittle when the pattern shifts. Classical Maya lowlands are an example. They were brilliant water engineers, reservoirs, causeways, terracing. But much of their political heartland depended on predictable wet and dry seasons feeding maize agriculture. When multi-decadal droughts hit between about 800 and 900 CE, many core city-states collapsed. Peripheral regions with more diverse ecologies and mixed subsistence strategies held on longer. Compare that to medieval Europe during the Little Ice Age. From roughly the 14th to 19th centuries, harvest failures, brutal winters, and weird summers were common. There were famines, plagues, witch panics, but Europe didn't uniformly break, partly because its agriculture by then was diversified across a wide latitudinal band, with different crops, different soils, and different local strategies. When grain failed in one region, another might still produce, and increasingly trade could move that surplus around. Which leads to the second trait, dense, redundant trade networks. The late Bronze Age palaces were plugged into long-distance trade, but their systems were narrow, controlled from the top, and heavily specialized. If tin from one region stopped flowing, bronze production everywhere stalled. By contrast, the Hanseatic League or later early modern Atlantic networks were messy, overlapping, competitive. If one merchant route failed, others could step in. If herring collapsed in one fishery, fleets moved to another. That redundancy made the economic system more shock-absorbent, even when individual communities suffered. Third, governance that could actually adapt. Sometimes this meant strong central states capable of rationing, organizing relief, or changing policy quickly. Sometimes it meant the opposite, devolved authority where local communities could experiment without waiting for imperial permission. Tokugawa Japan during the colder 17th century is a case in point. It faced famines and bad harvests, but also saw deliberate forest management, irrigation projects, and shifts in cropping patterns. Village-level institutions, samurai administrators, and the shogunate all played roles. The system wasn't humane by modern standards, but it was capable of learning. Where governance froze, societies cracked. Late Ming China hit by Little Ice Age cold, drought and flood, plus fiscal crisis and rebellion, is a textbook example. The state struggled to respond, local communities were drained by taxes and corruption, granaries failed to buffer food shocks. Climatic stress became a political crisis. Political crisis magnified climatic stress. Underneath all of this is a simpler, more brutal rule. Over-reliance on a narrow climate window is dangerous. Norse Greenland built a European pastoral society at the edge of what was climatically possible: hay meadows, cattle, churches, trade in walrus ivory. When the medieval warm period ended, and the Little Ice Age bit, they were boxed in. No easy migration routes. Few alternative livelihoods they were culturally willing to adopt. Inuit neighbours with far more flexible Arctic toolkits survived. The Norse disappeared. Other people, facing different squeezes, moved instead of dying in place. The so-called Sea Peoples at the end of the Bronze Age may have been, in part, displaced groups from drought-stressed regions. Germanic and steppe migrations during the late Roman period followed shifting ecological and political frontiers. In many cases, migration was not collapse, it was adaptation. Painful, violent adaptation, but survival all the same. Innovation played a similar role. New crops, like drought-tolerant millets, or later the New World staples of maize and potatoes in Europe, reshaped what was possible under cooler or drier conditions. New institutions, insurance, public granaries, futures markets smoothed out the roller coaster of bad years. New energy sources shifted pressure away from forests or marginal lands. What does all this mean for us, staring at our own uncertain reset window? Not that there's some magic checklist guaranteed to save every society. History is not a blueprint. The world we're in, 8+ billion people, globalized supply chains, fossil-fueled everything, a rapidly warming planet, is unlike any previous cycle. But the patterns offer perspective. They suggest that resilience is less about never being hit, and more about having room to move when you are. Multiple food sources, not just one highly optimized monoculture. Multiple trade routes and partners, not a single fragile pipeline. Political systems that can process bad news and pivot, instead of clinging to yesterday's assumptions about what the climate should be. They also remind us that fragility often hides inside success. The richer and more efficient a system becomes, the more tempting it is to prune away redundancy, to lock into the single best way of doing things for this particular climate, in this particular moment. If the long cycle tells us anything, it's that this particular moment never lasts. In the final section, we'll bring that lesson home. What does it mean to live inside a climate rhythm that we're now pushing and warping ourselves? What kinds of choices about energy, cities, food, and even stories we tell about risk and safety might matter when the next turn of the wheel arrives? Here's the uncomfortable place we've landed. For the last hour or so, we've been time travelling. We watched the Younger Dryas slam the brakes on the end of the Ice Age and nearly derail the birth of agriculture. We saw the 4.2 Kiloyear drought help topple Akkad and rattle Egypt. We followed the Late Bronze Age crash as a tightly tuned trade system shattered under layered stresses. We traced Rome's rise in a mild, stable climate and its long, uneven fall as conditions cooled, dried, and shifted around it. We watched 536 AD drop a curtain of dust over half the planet, then the plagues and famines that followed. We rode the medieval warm period into Viking voyages and cathedral-building booms, then watched the Little Ice Age grind back in, chiselling at Angkor, Ming China and Norse Greenland. Each of these wasn't just a bad century. They look, when you stack them, like beats in a rhythm. Roughly every 1,500 years or so, a phase shift. Not a perfect metronome. Climate never is, but a recurring drumbeat. Sudden coolings, regional droughts, ocean currents lurching, solar activity dipping, feedback loops kicking in, and in that rhythm, civilizations don't just rise and fall randomly. They cluster, Younger Dryas, a reset at the very edge of agriculture. 4-2K event, early states tested, some broken, some bent. Late Bronze Age, a globalized system for its time, cracked by drought and disruption. Roman warm period and its aftermath, one version of empire built on climatic luck, then stretched thin as the background pattern changed. Medieval warm period to Little Ice Age, expansion, experimentation, then contraction and recalibration. Not clockwork destiny, but a pattern of stress tests that arrive whether you're ready or not. So where are we in that long cycle? Bond events, the 1,500-year pulses we talked about earlier, aren't fairy tales. They're written in ice cores and ocean mud. The last big cold-leaning pulse was the Little Ice Age, peaking a few centuries ago. By that rough rhythm, we are not at the very start of a fresh, natural cold plunge. We're sitting in the long tail of the last one, except this time the script is different. For the first time in the whole 1,500-year story, one species is actively rewriting the boundary conditions, pumping greenhouse gases into the atmosphere, reshaping forests and oceans, building a civilization that assumes a relatively narrow climate band will hold. We're not just passengers inside the cycle anymore. We're leaning on the steering wheel. So here's the question that should keep us up a little at night. If past climate pulses could rewire whole civilizations, when humans were just reacting what happens when the next big natural swing arrives on top of changes we've already triggered ourselves? Do we get a softer landing because we're technologically powerful, globally connected, able to see trouble coming in satellite data and climate models? Or do we get a harder one because our food systems, cities and energy grids are more optimized and more brittle than anything Akkad or Rome or the Norse could have imagined? History doesn't answer that for us, but it does hand us a mirror. It shows that climate resets don't arrive as a single headline disaster. They come as decades and centuries of pressure, pushing on the weak points of whatever system we've built. It also shows that people who diversified, who kept options open, who could move, adapt, and cooperate across distances, were the ones whose descendants got to tell the story. That's why paying attention to these old cycles isn't just an academic hobby. It's a way of seeing our own moment more clearly. If you've made it this far, you're exactly the kind of person this channel is for. So if you want more deep dives into the hidden patterns behind history, climate, genetics, trade networks, collapses, and near misses, take a second to like this video, subscribe to the channel, and hit the notification bell so you don't miss what comes next. I'd also love to hear from you in the comments. Where in the world are you watching from? What does the idea of living inside a climate cycle look like where you are? Coastlines, heat waves, rivers, snowpack, all of it. And if you want to really support this work, the best thing you can do is follow the show on Spotify. There's a link down in the description. Listening there helps more than anything else to keep these long-form investigations going. We're standing at a strange intersection. A long, natural rhythm we barely understood until a few decades ago, and a human-driven shift that's moving faster than anything in the ice record. We don't get to step outside that story, but we do get to choose which kind of ancestor we want to be when the next turn of the wheel shows up in someone else's history.